Hello. Hey, Torsten. Georgios, are you able to hear me?
Hi,
Oh, hey,
we can
Torsten.
hear you.
Hey, good morning. How are you? Can you hear me?
Yes, we can hear you.
Good. Hi, Susanna.
Hi.
Nice to hear you. I'm sorry I couldn't be here. I'm back in the US, but for the last few months have been a bit difficult, so I decided to skip the in-person travel, although I'm not that far away. Let me just turn my camera on and just make
Yeah.
sure. Yeah, I mean, I can. So during the tutorial, I should just join as a speaker, correct? Sorry, as just the regular Zoom link that everybody uses for attending, and we start presenting when it's time, my time.
I think you can just join also as a host. You can join multiple times.
I see. Okay.
I just join as a host. I think that's easier.
Okay. All right. I will do that.
We still need to figure out how to get.
Yeah, we are solving some technical issues, how to make everything working here.
Okay. Let me know if you want me to test anything. Okay.
Yeah, sure. Thanks.
I'll join.
Yeah, the problem is that we need to really admit everyone as a whole to enter, and I don't think that I will have time to look at it every single second. Like
I will try to fix this.
Right.
We can try to set you up during the coffee break.
Okay, and I can also do that actually while the tutorial is going on. As people come in, you're saying, I let me join back as host, and then let me see if I can help you during the first part of the tutorial, right?
We'll try to plug your PC, and then I will plug my PC again, and so that we can try it the ones.
Yes.
Okay. So unplug it.
All right, I will rejoin as host. Bye-bye.
So I will then still, if you are, or there are still once try again. Okay. Once you will test it, I will still 1 minute for testing.
Can you all hear me? Wait a second. You're connected to Zoom? Are you connected to Zoom? Just to see, did you have headphones or something, just to see whether they can actually hear me, because I'm not so sure about the setup here. Yeah. Good. Okay, good morning. Can everyone hear me? Can the people on Zoom hear me? If yes, can you just put something in the chat so that we can verify this? Anyone, they can? Good. Okay. Welcome to the CVPR 2023 tutorial on large-scale visual localization. I'm Thorsten Sattler, and I'm co-organizing this tutorial with Yanis Afritis, who could unfortunately not join, Eric Brachmann, Susanna Kukulova, Mark Polyface, Zurib Dazinia, and Yorgos Tolias. This is a brief introduction, slightly behind time. We're going to start with Yorgos' part, which is on image retrieval for coarse localization. Then we're going to go to the second part, which will focus on feature-based localization. Susanna will first give some introduction over basic principles on camera pose estimation. We're going to do a coffee break. Then I'm going to talk about feature-based localization using the principles that Susanna introduced. And then Sudipta will talk about privacy-preserving localization. Then part 3, which is Eric, will talk about learning-based localization systems. And Mark will finally conclude about datasets and benchmarks. Yeah, and with that, I'll give the floor to Yorgos. Okay, hopefully I'm sharing my screen properly to everyone. And people should be able. No. So far, no. Try to. It looks as if I'm sharing. Yeah. It's not just showing. Where's that? Okay. Share screen and then desktop 2. No, I will do that. Right. Oh, no, you can see the kind do desktop 2. Let's see. Full screen. Oh, la, la, la. Stop screen. Oh yeah. Okay. Okay. Where did this window go? It's just because let's see. Okay. No. I'm logged out. Sorry everyone for the delay. It is organizers. Go to Zoom. You're still there. Just go. Okay. Do we need back to meeting? But okay. But something is wrong with multiple screens. I think. Yes. Let's just do stop meeting. Stop sharing. Okay. Right. Share desktop 2. Okay, let's hope this is working now, right? Jana, okay. I think we're set to go. Okay. Hi, everyone here in the room and people that are attending online. I'm Yorgos Tolias from the Czech Technical University in Prague. So other talks in the tutorial, we'll talk more about precise localization in the form of 6D camera pose estimation, while in this part, I'll talk about coarse level localization in the form of place recognition and how to handle this as instance retrieval. So place recognition, we will talk about place recognition in the form of given a test image. We want to predict the GPS coordinates where this image was taken and localize it on the world map, or identify objects that are depicted in the image, like in the form of known places, named locations from a long list of such locations. So just to put some context in the form of datasets and benchmarks that are existing and we typically work on, the datasets that are dealing with GPS estimation, where we have a large collection of images with known GPS coordinates, and then given a test image, we are supposed to make predictions for the GPS coordinates. So in essence, it's a regression task. Or other datasets where each class is a specific building or known landmark, and the underlying task is a classification or a retrieval. And in some of these cases, the number of classes reaches the order of hundreds of thousands. So the task is characterized by a huge number of classes. So in the sense of its name or known location, its known landmark, or the space of GPS coordinates when we will do some form of quantization. And its cell in this quantized space is a class. It's also characterized by low intra-class variability. So this variability comes typically from viewpoint changes, illumination changes, background clutter, and occlusions, while it's also characterized by large inter-class similarity. So these actually characteristics make it close to a very mature field, this of instance level retrieval, large-scale instance level retrieval, and we're going to approach place recognition through retrieval approaches. So in the sense that given a test image, we are identifying the most similar images from a large collection of images, hoping to retrieve, to top rank the most relevant elements. And then with these relevant elements, one can do nearest neighbor, use nearest neighbor classifier approaches or kernel density estimation to predict the GPS coordinates. Here in this talk, we're not going to cover like how to use these approaches, but we're focusing on the part of retrieval. So there is two-step approach, typical two-step approach, where we're extracting some representation from all the database images. So this is some form of indexing of the large collection of images. And then given during the query time, we do the same for the query image. And it's all about estimating this scalar image-to-image similarity between the query and every item in the image collection, rank the images, and obtain the top rank ones. In the simplest form, it's a top one classifier where we assign the GPS coordinates, for instance, of the most similar image. And in the follow-up, I will talk about this estimation of the image-to-image similarity, focusing on two parts, the representation part and the way to match compare the image representation. It is quite common to handle this through global image descriptors. So we have a function H that takes an image as an input and maps it to a high-dimensional vector space. So this function H can be fully handcrafted or it can be a learnable model. The benefit here is that in this way, instance retrieval reduces to
nearest neighbor search in high dimensional spaces. There is tons of approaches that someone could use to do this efficiently, and it's also compatible directly with dimensionality reduction approaches and so on. Another family of approaches is instead extracting a set of local descriptors to represent an image, which are typically known to be invariant to some transformations, also are more able to handle partial matching because of occlusion or a lot of background clutter. And in that case, instead, what we need is a way to compare a set of the vectors with another set of vectors and obtain the scalar image-to-image similarity. So this kind of approach can typically be more effective, but they're also at the same time much more costly than the case of global descriptors. And in large-scale image retrieval, one would have to index those local descriptors and store them separately. So the memory requirements increase dramatically. A common way to approach the task of estimating image-to-image similarity with local descriptors is through such a match kernel formulation, which is in a sense a voting approach. So what we do in this case is we cross-match, we explicitly enumerate all possible pairs between the two feature sets. And for each pair, we can see this as correspondence between two local descriptors, two local features. We accumulate a similarity vote. And to do that, we typically have an embedding function. So we take each original local descriptor and we map it to a potentially higher dimensional space that is more discriminative. And at the same time, we have a local similarity function that is responsible of comparing these two embeddings and inferring the similarity for this correspondence, which we accumulate to obtain the image-to-image similarity score. You might see that I often use a symbol for proportional here because I'm skipping the typical normalization that is there for this similarity to be meaningful. So there is a special case of this local similarity function that make the two families of approaches, the global descriptor case and the voting approach, is equivalent. And this is when this similarity function is a linear operation, such as simply a dot product. Because in that case, we have the voting approach that explicitly enumerates all the possible pairs and accumulates the votes. But because of the linearity of the operations, we can reorder the terms and becomes equivalent actually to a global descriptor, which is the outcome of aggregating the representation for all local descriptors. So the benefit here is that we have a global descriptor, an efficient way to compute the similarity, simply a dot product between global descriptors. But this is equivalent to a voting approach that is more costly, and it's also like intuitive about how the image-to-image similarity is estimated. So here is a very common, widely known example of an approach that can be described by this formulation, which is the VLAD descriptor, the vector of locally aggregated descriptors. So this is an extension of the well-known bag of words model, where we're dealing with quantization of the descriptor space in the form of a visual codebook, for instance, computed with k-means on a large collection of local descriptors. And now this embedding function G that I described before, that I mentioned before, is actually corresponding to a very high dimensional vector that is very sparse, where in the corresponding subspace, we encode the residual vector, which is the relative position in the descriptor space of descriptor X with respect to the visual word, to the centroid in the visual codebook that this local descriptor is assigned to. So this is an extension of bag of words in the sense that in bag of words, typically we just accumulate how many descriptors are mapped to a visual word. Here it is much richer information that we also encode the relative position within this centroid. And just to revisit the same point of view again, so the benefit here is that That's how we compute the blood descriptor. We accumulate these high-dimensional embeddings. We end up with a vector per image. And when we compare two images with dot product, essentially, we are enumerating all the possible votes in an implicit way. And how the quantization affects this voting is that we will have non-zero vote only if the two descriptors, X and Y, from the two images, are mapped in the same visual word. And the strength of the vote will be according to the positions within the cell. So typically, this approach is meaningful with small codebook sizes, because often we're dealing with a few hundreds or a few thousands of features per image. So you can easily imagine that if we have a much larger, a very large codebook, the representation becomes super sparse, and it's not necessarily meaningful to handle it with a global descriptor, that is very sparse. On the other hand, there are other kinds of approaches that are meant and are designed to work with a much larger codebook and very fine quantization of the descriptor space. So this is the case of the aggregated selective match kernel, briefly as ASMK, where first, here we do the work only for the common visual words between two images. There's pretty much nothing to vote when there's no common visual word between the words. And for each visual word, what we do, we again work with the residual vectors, but we aggregate them all together in a single representation. So we aggregate and renormalize. So this is essential because there is a benefit by not enumerating now all the possible votes within the same visual word, because features mapped to the same visual word, typically correspond to a similar structure or object part, and we don't want to end up with some kind of overcounting. So in that way, we have a single vote that we accumulate per visual word and not more than that. And what is an important ingredient here, and is actually also the factor that breaks the equivalence between the two families, the global descriptor and the voting approach, is this nonlinear now local similarity function, which includes some thresholding by totally rejecting and not accumulating the weak votes, and a monomial kernel that actually tries to boost the contribution of the stronger votes. So it might look too simple, but actually such a voting function is a game changer. Just increasing the value of alpha from 1, the linear case, to 3 gives noticeable boost in performance. Of course, there's the cost now that we cannot anymore do the work with a global descriptor because there is no equivalence. So we explicitly need to enumerate all the possible votes. But luckily, the good news is that such an approach is compatible with indexing the local descriptors with inverted files, which make the search much more efficient. So here we simply see with the same color local features, locations of the features that are mapped to the same visual word. And this is typically the case for repeating structures. And this gives an idea what is the benefit by this aggregated residual vector, that we will only assign a single vote for the same color instead of ending up with really doing some overcounting and letting these bursty features to dominate the image-to-image similarity. So these kind of approaches have been developed back in the older times with classical approaches and handcrafted local descriptors. Nevertheless, they are compatible in an off-the-shelf way with other kind of local descriptors as well. Now it is worth switching to what someone can do in an end-to-end way on top of deep network architectures. For instance, the case of convolutional neural networks. So here we see we're dealing with a fully convolutional network, which is our feature extractor. And we see the 3D tensor of activations as a set of local descriptors extracted in a dense way. So at every location, we have a different local descriptor. And now things that I described before can be applied here as well. So in the simplest form, we have a different embedding function G, another embedding function G, and we accumulate this to end up with a global descriptor. And what happened in the literature is often that we borrow the classical approach and modified it so that it's trainable in an end-to-end way. That was the case for NetVLAD. That was an extension of the VLAD approach. A difference was that instead of doing hard assignment of a feature to a single visual word, there was some soft assignment process, assigning with a weight to all the visual words, so that, in a sense to say, there is richer information with the gradients during backpropagation, so that the centroids of the codebook that are now trainable parameters are getting updated. Now, what is interesting is that something that was not really effective with handcrafted local descriptors such as Shift, just accumulate them all and obtain a global descriptor, is really like performing very well in the case of CNN descriptors because of the higher discriminative power. And that's the case of just performing sampling of the descriptors. So this is equivalent to the very widely known global average pooling, let's say, layer that is typical at the very end of a deep network architecture. And if we analyze the pairwise image-to-image similarity, actually this is the hopefully known to us now match kernel where we are accumulating all the votes. So doing global average pooling and then compare the global descriptors essentially cross matches all the activations at all the possible locations of the images. An interesting extension that has appeared in the literature is the introduction of a saliency score, an attention score, that is a scalar that is meant to weight the descriptor before accumulating them. And this has been in the form of handcrafted attention weight, or also learnable by an extra layer. So again, it is worth checking how the image similarity is composed, which is now again cross-matching, accumulating of all the votes. But now there are the saliency scores that are meant to downweight the votes according to how important the feature is, let's say if it's background or foreground, in a simple sense. Of course, simply instead of using global average pooling, there has been also work and descriptors. MAC descriptor stands for maximum activation of convolutions, where we use global max pooling. So what we do here is that we see this 3D tensor of activations now as a set of 2D activation maps, one for every convolutional filter. And we simply store the maximum activation in the global descriptor. Now, because each activation here corresponds actually to an area in the image equivalent to the receptive field of this activation, when we compare two such descriptors, we can interpret it as working through some implicit region correspondences. And we can have we can see that dimensions of the descriptor that contribute a lot to the similarity, if we map the corresponding receptive fields, actually corresponds to typically similar regions on the pair of images. Now, an extension of these two descriptors that I mentioned before is the generalized mean pooling, which essentially extends, it's a generalization of max pooling and sum pooling, where we raise to the component-wise power of P every descriptor, average the descriptors, and then raise to the component-wise power of 1 over P. So simple to see that when P is equal to 1, this is equivalent to sum pooling and the Spock descriptor. When P tends to infinity, it approximates, it tends to max pooling. And so in some sense, if we see how the activations of this part here before the aggregation look like, the descriptor tends to be much more localized when P gets higher, and P can be hand-tuned, cross-validated, or is a learnable parameter during the training. A more hybrid approach is when we have a sliding window process, and from every window, we extract MAC descriptors, and then we aggregate them. So this is the so-called regional MAC descriptor in the literature that we proposed some time ago. Now, all these can be easily used and have been originally used for transfer learning. We take the network that is pre-trained on ImageNet and simply repurpose the architecture by adding these layers at the end. And they have been performing quite well. Nevertheless, when we end up fine-tuning this representation for instance level retrieval task, there is noticeably boost of performance. And in practice, we have seen that the GEM descriptor has been easier to be trained and achieve higher performance than the ArcMac, which in the off-the-shelf way was performing better. So global descriptors are easier to train, they're efficient for searching, and they're compact memory-wise like representations. While local descriptors are better in matching to handle occlusions and clutter. So we have worked a few years ago on a principled way to train local descriptors, but with image level labels. So we only know relations between whole images and not like for the regions of the images themselves. And we did so through metric layering of global descriptors. So we have the standard architecture that I described before, an image map to a global descriptor, and we're trying to push descriptors of relevant images close to each other, of non-relevant far away. And it is helpful to take a closer look again on the Spock descriptor and the sampling operation. So here, after the fully convolutional network, we sample all the descriptors and end up with a global descriptor. So dot product between such cases is decomposed into cross-matching and the standard voting approach. So in a sense, if we optimize global descriptors, we implicitly optimize the local representation as well. And what we did in this work, we extended the architecture so that we amplified the local descriptor training. So first is that we applied some local smoothing, just a 3x3 like average pooling filter that we observe how it improves the synergy with the ASMK approach that I described before. We can see some results later on. Of course, some necessary dimensionality reduction because typically the depth of the activation tensor is very high, and there was a benefit that we could actually initialize this layer with a result of a closed form solution that was quite handy for the training to start already at quite high performance. A non-parametric attention function to use it as a weight in the sampling operation. And actually, we ended up using a non-parametric attention function, not a learnable one, but simply the L2 norm of the activations at every position did the work pretty good without adding any extra parameters in the learning. So, and again, when we do the cross-matching, when we compare two global descriptors, essentially we're optimizing all these votes here between local descriptors and the weights themselves. So in a sense, the weights now can control the contribution of the local votes. During training, we apply this architecture, these functions that are described as in the training phase. But now the difference is that we use the attention score to form a local feature detector, and we simply maintain the local features with the largest strength, the largest attention value, and then we index those to use them with the ASMK approach. So now what we achieved is that despite the fact that we were relying on image level labels, we ended up training a local descriptor extractor together with a local feature detector. What is interesting is that if we observe how the performance of the global descriptor changes during training, this would be the red curve here, and then we repurpose the network and we use it for local descriptor extraction, this ends up in a much higher performance. Of course, because now we're using it in a much more costly way to do the image to estimate image to image similarity through a matching approach. So what is interesting is that typically such a discrepancy between training and testing architectures in the literature in many other tasks results in drop of performance, but this is not the case here. So this work that I presented was inspired by the Delft descriptors proposed by Google. And actually we can take a look on how the differences of this architecture affect the performance. And of course, what makes sense is not to focus just on the retrieval performance itself, but also on the memory requirements, because we are supposed to be indexing a large set of descriptors per image, and this requires memory. Also, it affects the query time. So ideally, an approach should be mapped on the top left corner, high performance and low memory requirements. So our own implementation of Delph, so that to keep things equal, starts here. And then just by switching from a classification loss to a metric learning loss, like the contrastive loss, gives a noticeable boost in performance. It also compresses the memory. So this is a bit more than, in my view, changing from one loss to the other, because this metric learning point of view is closer to the perspective of cross-matching local features, because we are comparing two images which are explicit aggregation of local features, instead of matching an image with just a learnable vector per class. The non-parametric attention function is also a beneficial term, while the dimensionality reduction doesn't change things much, but still it's very beneficial because of the reduced complexity that it offers. And the local smoothing is a game changer instead of in terms of memory requirements, because it smoothens a local neighborhood of local features, which in the end up being mapped to the same visual world. And with the SMK approach, they're represented by the same vector. So this has benefits in terms of memory requirements. So when dealing with local descriptors, we have an easy way to form tentative correspondences, as we call them, between two images, simply by nearest neighbors of local descriptors, or by considering the quantization of the descriptor space. So two local features mapped in the same visual world are in correspondence. And ransack-like approaches have been offering a very intuitive way to re-rank the images, which is the number of inliers, a number of correspondences that follow the same geometric transformation. And this has been a standard practice in the literature for a long time, that was effective also with local descriptors that were learned with deep architectures. What is interesting is that also there have been learnable approaches in the literature to do this kind of matching. This is the case for the re-ranking transformer, where pretty much uses a transformer architecture in an off-the-shelf way by feeding in the input the concatenated set of local descriptors for the two images. So internally in the attention layers, now there's this cross-matching. So the attention represents the cross-matching between all features. And there is multiple layers of those, and the typical CLS token, on top of which a binary classifier is applied. In the end, for a binary classification task, are the two images matching or not matching? So while in this case, in this approach, the input is the set of features and the correspondences are formed internally to the transformer in the attention matrix, there is actually an approach in the main conference this year that is dealing a bit differently with that. So of course, they're also using VITs, but still this is a way to obtain your local features. And with an attention score, only the top features are kept. But first, the correspondences are explicitly computed in a correlation matrix. And the strongest correspondences are maintained here, the strongest 5 correspondences per local feature. So now it is the correspondences that are fed to a transformer, to some transformer blocks. So in a sense now, in the attention matrix, now we are cross-matching not the features, but it's a second order process that we're cross-matching the correspondences. And these are represented by the locations of the features and by the strengths of the features. So at high level, like consistent groups of correspondences are, let's say in an abstract way, are detected and are weighted internally in a transformer, so that someone can learn again a binary classifier to infer whether the images are matching or not matching. Now I'm switching a bit to talk about the losses that we used during the training, about some of the approaches that I described. So for instance, in the case of global descriptors, it is more or less straightforward and common to use a classification loss like cross entropy or the arc phase loss that comes from a different field has appeared to be very effective that optimizes the maximizes the decision boundaries in the angular space. Now, a drawback is that first, these approaches are not applicable to the pairwise similarity measures, some that I described before, but only in the global descriptor approaches. And another is that essentially we have to rely to categorical labels now, to class level labels, but still we're trying to learn an instance level similarity measure. So that's not necessarily the best way to go. There is a subcenter arc phase loss that is an improvement of that, because each class now has multiple learnable vectors. And when a class is multimodal, you will actually end up assigning the vector to just the closest subcenter of the class. What is more appropriate are, from an instance level point of view, are the pairwise loss functions, widely known, such as contrastive loss and triplet loss, that operates on similarities or distances between pairs of images. And typically what we have seen that is much more essential not to rely on class level labels, but to have an automated way to infer whether like two images show the same view of an object or not. And for instance, like 3D reconstructions with structure from motion approaches have been a very good source of training data for doing that. So in some sense, this is a hand design approach that we assume that it reflects the objectives of the task. So there have been more principled ways to actually optimize the retrieval evaluation metric. There are commonly established retrieval evaluation metrics. So in our work at CVPR last year, inspired also by previous work where they were optimizing the average precision metric, we instead optimized the recall at the top K images, which is originally a non-differentiable metric. So we'll get a closer look of how we do that. So we have a query image and a set of database images. We estimate the similarity between query and all the images. To estimate the recall, we first sort them, and we count how many images are ranked before rank K. So for instance, recall at 2 would be 1 out of 2 in this case. Now let's see this from a different point of view. What we need to estimate is the ranking of its database image with respect to the similarity to the query. So if, let's say, we focus on the ranking of this image here, yeah, what one does is compare the similarity of this image with the similarities of the other images, pass them through a step function. This tells us whether the other similarity is larger or smaller. We accumulate the outputs, and this gives us the ranking in the whole ranked list. So that's a different point of view of how we end up with the sorting that recall at K requires. And then, given the ranking that we already have, one needs to just compare with the value of K and see, pass it through a step function, accumulate the result, and now estimate how many images are ranked in the top 2 positions. 1 over 2, recall is 0.5. Probably you already see what is happening. There is a step function here that doesn't allow us to use it during training. Maybe you see this happening, that we use a sigmoid function to approximate that. And there is a trade-off here, that we want a good approximation of the recall metric, which means that we want a picky, we want a steep sigmoid function, yeah, to have a good approximation. But this has like a large range of 0 gradients, so that's not useful for training. And there is a trade-off, and we need to use a smoother one, but of course compromises the amount of the approximation and how good we estimate recall. There is a trade-off there, and actually this temperature is something that we typically cross-validate. It's one extra hyperparameter. And in practice, we see that consistently we obtain better results with such a loss function compared to the standardly used contrastive in a, let's say, in a very well-tuned version of the contrastive loss. So what is very useful, what is necessary actually, is to work with very large batch sizes so that recall metric is meaningful and represents what happens in a large-scale retrieval system. Of course, there is memory constraints here. We cannot easily fit many images to the GPU, so we actually just borrow an implementation trick for the ICV19 paper here by researchers at Naval Labs in Europe, which is a three-step approach. First, we do a forward pass and we obtain all the descriptors, the global descriptors for the images in the batch. Then we just give the descriptors and completely discard whatever, all the internal representations of the network that need to be maintained in memory. We proceed with the estimation of the loss, and we have the gradients now to the level of the descriptors. And now we have a third step of another forward pass, which we could do even image by image, and then backpropagate the gradients up to the initial point. This is actually quite a useful implementation trick, not only for such approach and loss, but also for many different tasks. We managed to work with batches of 8,000 large resolution images on a single GPU. When I say large, I mean like to the level of 1,000 pixels times 1,000 pixels. So I'm switching now to one last, a bit different part, to talk about the fact that instance level retrieval, instance level matching is typically a task where details matter on the objects themselves. Therefore, we investigate what is the impact of the image resolution in that case so that we better capture the details that matter. And one can train on a particular image resolution, a maximum resolution of 512 times 512 pixels. But during test time, actually, you can vary the resolution during which testing, and we see that there can be benefits by testing on larger resolution. Let's say it happens if we train on different resolution. There is some dependence like between the train and the test resolution. So in the sense that we might not keep having benefits if we go very far from the resolution that the network is trained on. And we see that on the top left corner, there is the highest performance that we can achieve. So nevertheless, the problem is that processing large resolution images has cost in descriptor extraction for the database, but most importantly for the query itself, because it affects inference time. So retrieval is a pairwise task. We're comparing two images. We have the database side and the query side. So simply, we propose to estimate similarity in an asymmetric way, where we use large resolution images on the database side, but we have the ability to process the queries on smaller resolution. So this can typically be useful when you have large image collections processed with at large resolution to have a better representation, but you might need to access this from low resource devices as well. And one simplistic naive solution to that would be that you actually can use the same network, but we have introduced a discrepancy between the scale that the objects appear to. So in order to compensate for that, we end up like using the same architecture, but learning different weights per network so that we can compensate for this discrepancy and align the representations in the two cases, the database of large resolution and the query of smaller resolution. In the literature, there has been also asymmetry in the sense of using a different network, which is also typical practice in other tasks as well. So what actually we observe in this work is that optimizing the performance versus memory trade-off is done in a much better way through resolution asymmetry than network asymmetry in this particular task where details matter. And we do that with a distillation approach. So we consider a teacher network, which is actually the given network that is used to process the database images at large resolution. And we want to learn a student network that will process the queries at smaller resolution. So we initialize one by the other. And we see that actually that's quite a useful thing to do. And we can do that because we're using the same architecture. And we perform distillation in an unsupervised way. We apply a loss per particular image, which we downsample to be processed by the query network. And what is important here is to apply augmentations, but to apply augmentations in a coupled way. So we want to process, we want to have exactly the same input for both networks, just a different resolution. So there's no desire here for like obtaining any extra invariance. It is just discrepancy. If we do different augmentations, it's just discrepancy between the two spaces. What we gain is that just we augment and have like many more inputs for the two representation spaces. And the goal is actually to align the two representation spaces based on the embeddings produced by the two networks. So simply to show here, we have one image augmented 3 times. The teacher representation is fixed. So the crosses here are fixed. So we want to make the triangles move to the crosses. So we align the spaces through sampling as many points as we can from the training set and through augmentations. So how this happens here is that we cross-match actually all the vectors, and we focus on the diagonal of this matrix, which is the self-similarity, but in an asymmetric way. And we want to optimize that. We want to have it equal to 1. So this directly reflects the objectives of the task. Nevertheless, we go one step further. We cross-match also the representations within the same space, and now focus on the off-diagonal elements, which are actually the pairwise similarities, and we want to apply some consistency between these pairwise similarities across the different spaces, like asymmetric with symmetric of the teacher, and symmetric of the teacher with symmetric of the student. Now to go back to this toy example, this is equivalent to having these two pairwise similarities, and we would like them to be consistent, as similar as possible to the asymmetric ones. And we do the same process for all the points. And the last part is that we want also the similarities that we see there within each of the spaces to be the same. Maybe someone could see that actually just optimizing this objective doesn't satisfy the objective of aligning the two spaces, while this directly satisfies that. Nevertheless, we see in practice that this acts as useful regularization and gives a performance boost. So it's all about the trade-off between performance and the cost of processing the query. And we measure that by the gigaflops of processing the query with a network that is trained to operate on large resolution, and we apply it in a symmetric way, large resolution for the query and the database. Or we can do the same at a smaller resolution, which compromises the performance. A simplistic way is that we use the same network as this one, and we simply downsample the query, which noticeably compromises the performance. Like it's a faster way to process the query. Nevertheless, the performance is noticeably harmed. While with the distillation approach, we see that there is big benefit in the performance while maintaining the same, of course, complexity benefits. And so we got speeding up benefits by this asymmetric approach, which is maybe a special flavor of what someone would want to do for retrieval in a retrieval task. So what is also interesting is that we tried the same student network that we learned through distillation in a symmetric way. And that's the result that we obtain. So compared to this symmetric setup, there is an improvement. So to summarize in a different way, it is instead of directly training the representation at small resolution, it is better to train it at large resolution and then distill down to smaller resolution. And there are performance benefits with that, while the complexity cost remains the same. And in results that I'm not including here, we have seen how it is noticeably better to optimize this trade-off with resolution asymmetry than using different network architecture for the query. And the fact that we can initialize them to be the same appears to be a game changer. Now, just to sum up, because the whole talk was about handling coarse localization, place recognition through retrieval. What is a comparison with classification approaches? And the standard approach has been the planet approach, where the space of GPS coordinates is quantized and the deep network classifier is trained. So the big benefit here is that that's a very compact model to localize images all over the Earth. There was a very interesting work that was comparing this with retrieval approaches. So this classification, this planet approach, is very good at coarse level localization, but coarse level is quite coarse, let's say. It's at region or country level. So while at fine level, it is not that good, but it's very compact. So just using the representation that is learned through retrieval improves performance a lot at the fine level. But if someone tries to fine tune with this, let's say, categorical labels and the pairwise loss, there are no improvements because there is high intra-class variability within each cell of this quantized GPS space. So what turned out to be the best approach is get the representation from another approach that is trained with precise information about whether two images show the same view of the object or not. And this generalized much better in this task, handled through retrieval. And just a quick mention that there is also a method taking the best of both worlds, and actually it can be seen also like a way of ensembling this kind of approaches where you first predict a cell and then do retrieval and some extra filtering to obtain the final prediction. So that brings me to the end. I'd be glad to take any questions or also like stay extra and discuss during the break. So thank you for your attention.
You touched on it at the end there, but I was curious about how the image retrieval extends to whole world approaches for localization. And it seems to tie in with the classification methods. Maybe explain a little bit more how.
Okay. Yeah. Okay, it's good to see this in the, again, trade-off of performance versus memory, because the retrieval approach is essentially a non-parametric approach. So every single example needs to be indexed. There is a representation to store. So that's, let's say, a drawback when you have to index the whole world. So it really matters to have compact representation that can handle all the challenges of small objects, the variability of objects, and so on. So that's a drawback. Nevertheless, empirically, we observe that these approaches perform well at street level localization. So the achievement of Planet is a super compact model to do that. So yeah, they stand at a very different area of the performance memory trade-off. Okay, thank you for your attention. We continue with the next talk by Zuzana Kukelova.
You see it proper? Okay, I think it's okay. It should be okay. I think I hopefully. Yes. Okay, so hello, my name is Zuzana. Welcome to the second part of the tutorial. In this part, we are going to look at feature-based visual localization techniques. These algorithms actually establish some 2D to 3D matches between features in the query image and 3D points in the scene. And these matches are then used for camera pose estimation. And this is usually done by applying some absolute camera pose solvers inside some RANSAC framework or RANSAC loop. So in the following, I will just briefly introduce such camera pose solvers, which are core components of such feature-based visual localization techniques.
You can close the microphone.
Yeah, sorry. Is it better? Okay. Okay, so camera geometry problems like relative and absolute pose estimation play an important role in computer vision applications. For example, in localizations, 3D reconstruction, SLAM systems, augmented and virtual reality, and autonomous driving. Camera geometry solvers are usually used inside some RANSAC-style hypothesis and test frameworks. Here, the number of samples that needs to be tested actually exponentially grows with the number of point or line correspondences used for the estimation. For efficiency, it is therefore important to employ minimal solvers that generate the solution from a minimal number of such correspondences, point or line correspondences, and using all available constraints. Moreover, such minimal solvers also return correct geometry, for example, correct rotation matrices. We don't need to do anything after this. These minimal solvers are used inside RANSAC to obtain initial estimates of the geometry and the inlier set. On the other hand, there are non-minimal solvers that are usually used for refining pose estimates and inlier set in some local optimization, some LO RANSAC step. As I already mentioned, camera geometry solvers are core components of localization as well as structure for motion pipelines. And in this tutorial, you will see a lot of nice examples and videos from these localization applications. So here, I want to show you one nice video from closely related application, like 3D reconstruction from images. 3D models like the one that you can see here in this video are actually important parts of such visual localization pipelines that we will discuss in this tutorial. Here you can see an example of really large-scale 3D model, 3D reconstruction, and this reconstruction was created using reality capture, 3D reconstruction software from Capturing Reality, a startup company founded by my former colleagues from Czech Technical University in Prague. Now this company is part of Epic Games. So in this case, the 3D model was actually created from, I think, almost 100,000 images, and the final 3D model contains, I think, something like, or there's, I think, 30,000 images, sorry, and it contains something like 100 million triangles. And this was created on standard PC in a couple of hours. And this software uses a lot of such camera geometry solvers for calibrated as well as uncalibrated cameras, including several solvers that I will present in this talk. So in this talk, I will focus on absolute pose solvers, since these solvers are more frequently used in localization pipelines. However, I will first briefly review relative pose solvers. So in relative pose solvers, we want to estimate the relative rotation and translation or motion of a camera. And this problem is also known as the problem, you most likely know it, as the problem of estimating epipolar geometry. Relative translation can be, in this case, estimated only up to scale. So we have, for calibrated perspective cameras, we have 5 degrees of freedom, 3 for the unknown rotation and 2 for the unknown translation direction. So we need 5 2D point correspondences to solve this problem. And the first solution for calibrated perspective cameras that uses really the minimum number of 5-point correspondences was proposed by Krupa already in 1913. And this method actually returns up to 11 solutions to this problem. In 1981, Long and Higgins actually introduced the notion of the essential matrix together with some non-minimal algorithm, non-minimal method for its estimation using 8-point correspondences. And in 1988, it was shown that this problem for calibrated perspective cameras has actually at most 10 distinct solutions. Later, Nister was the first who proposed a really efficient solver that really returns just up to 10 solutions to this problem. This algorithm is extremely efficient. It runs approximately like, I think, 5 microseconds, depending on the implementation, and is still the state-of-the-art solution for calibrated relative pose problem. So Nister solver requires that the two cameras are calibrated. After the introduction of Grabner basis and algebraic methods to the computer vision community, it was I think around 2005, there has been quite some work on relative pose estimation for partially calibrated cameras, like cameras with unknown focal length or cameras with unknown radial distortion. Moreover, new solvers are still appearing. For example, recently Magnus Oscarsson revised different relative pose solvers for cameras with unknown radial distortions. Sometimes, especially for more complex geometries, minimal problems can result in very complex systems of polynomial equations. And for some problems, like the problem of estimating the relative pose between two cameras with different radial distortion parameters, actually non-minimal solvers, usually minimal plus one solvers, can be orders of magnitude faster than minimal solvers. Therefore, for a wide range of outlier ratios, such non-minimal solvers can result in faster ransack times, as their higher efficiency usually more than compensates for the large number of iterations that you need to do inside ransack. So sometimes minimal solvers are better, but sometimes it's better to use these minimal plus one solvers. Despite recent progress in generating really efficient polynomial solvers, for some relative pose problems, like the problem of estimating the relative pose of two rolling shutter cameras, efficient solutions are not known. So it's still unsolved, it's not fully solved problem. The main reason is that these problems result in very complex systems of polynomial equations that are not really efficiently solvable, even when you are using sometimes these minimal plus one correspondences. Okay, so this was just some short introduction to relative pose solvers, and now I will move to absolute pose solvers. They are really more frequently used in localization pipelines. So absolute pose estimation is the problem of determining the position and orientation of the camera from an image of a known object or scene. So in this case, we are using 2D to 3D correspondences compared to these relative pose solvers where we have 2D to 2D correspondences. This problem actually predates modern cameras. Already in 15th century, Leonardo da Vinci wondered how to determine a painter's eye viewpoint from a perspective painting. And later in 1715, Taylor, also known for the concept of Taylor expansion, developed an algorithm to estimate both the focal length and principal point of an imaginary camera, some observer, from an image of a cuboid together with the side length of this cuboid. In some sense, this is a very early prototype of these modern solvers that can jointly estimate camera intrinsics and extrinsics. So I will start with the easiest case, like the case where the intrinsic calibration of the camera is known, which most likely most of you know. So in this case, we want to compute the rotation and translation, the transform points in the vertical coordinate system into the local coordinate system of the camera. So we have 6 degrees of freedom. We have 3 degrees of freedom for unknown rotation and 3 for unknown translation. And in this case, each to 3D correspondence gives us 2 constraints in the form of the projection of these 3D points into the image. And these constraints have the following form that you can see here on the left. And since we have 6 degrees of freedom and each correspondence gives us 2 constraints, we need 3-point correspondences to solve this problem. So this problem is well-known P3P problem, and the solvers are called P3P solvers. P3P solvers have a long history. Already in 1615, Snellius actually provided a solution for special case where the 3D points and the camera lie on a plane. And later in Lagrange in 1773 was the first to sketch really a general P3P solver. Another well-known solution is the solution from Gruner from 1841. And I think in computer vision community, one of the best known solutions is the one by Fischler and Bose that was introduced in their ransack paper in 1981. Despite this history, actually P3P solvers are an active field of research. With the current state-of-the-art solvers from 2018, and there is even one at this year's CVPR. So you see that people are still trying to improve these P3P solvers. P3P solvers for calibrated cameras are actually extremely efficient. For example, this current CVPR solver runs approximately, I think, 220 nanoseconds. So they are therefore used in many applications. So most likely, most of you are using such P3P solvers for calibrated cameras. However, in many situations, the internal camera calibration is unavailable or is only approximately known. Examples of such applications are 3D reconstructions from photo community collections, which often do not provide camera calibration. Another example is localizing historic photos and paintings or handling zooming cameras with variable focal length. This creates the need for jointly actually estimating the camera pose and the camera intrinsics. So now let's look at such solvers that can estimate camera pose together with these camera intrinsic parameters. And let's start with the simplest case, the case where only the focal length of the camera is unknown. This is a reasonable assumption since principal point and skew can usually be considered to be known or approximately known. In this case, the projection equation for an uncalibrated camera with unknown focal length has the following form, as you can see here, where R and T are the unknown rotation and translation, and this is the unknown focal length, and alpha I is the unknown depth of the point xi. So in this case, we have 7 degrees of freedom, 3 for the rotation, 3 for the translation, plus 1 for the focal length. Therefore, since each point correspondence gives us, again, 2 constraints, we need 3.5 point correspondences to solve this problem. In this case, compared to P3P, this problem results in significantly more complex equations because you are multiplying your unknowns with this unknown focal length. This problem for the absolute pose problem for unknown focal length cameras was solved for planar scenes already in, I think, 1995. And in 1999, Trix proposed the first solution for non-planar scenes. Later, there was a solution proposed by Bujňák in 2008, which was actually the first robust and efficient general solution. And this solution is using efficient Gribner basis to solve this complex system of polynomial equations. All these solutions that I mentioned are actually non-minimal in the sense that they are using constraints from 4-point correspondences, not really from 3.5. And there exist like 2 solvers that are really using 3.5-point correspondences, one from Wu and one from Larson. The currently most efficient, or to my knowledge, this is the most efficient solution to this absolute pose problem for camera with unknown focal length, is the solution which is based on an efficient solver for 3 quadratic equations in 3 unknowns, also known as 3Q3 solver. This solver runs approximately 2.3 microseconds, and it returns up to 8 solutions to this problem, but is restricted to non-planar scenes. However, since this solver works really well for close to planar scenes, this is usually not an issue in real applications, and such solver is really used in real applications, even if we don't know in advance whether we have planar or non-planar scene. A good implementation of this solver is available in Victor's Larson POSIB library. In many situations, wide field of view cameras offer some advantages, like more stable pose estimates, or the ability to observe a larger region of space, and therefore also higher robustness to occlusions or illumination changes. In order to cover a wider field of view, these cameras usually exhibit large lens distortion. Usually it's dominated by radial lens distortion. And since we might not be, again, able to calibrate these cameras in advance, this creates the need for absolute pose solvers that can handle also such unknown radial distortion parameters. So in this case, the projection equation for an uncalibrated camera with unknown radial distortion and unknown focal length, which is using, in this case, so-called 1-parameter division radial undistortion model, has the form that you can see here. So here lambda is this new unknown undistortion parameter from this one parameter division model. Actually, this one parameter division model is a very popular model in camera pose solvers, and it's used in almost all minimal solvers, since it provides a good trade-off between the accuracy and model simplicity. It can handle even large radial distortions. For example, it's a very good model for a distortion that appears in GoPro cameras. So in this case, we have 8 degrees of freedom. We have unknown focal and rotation translation, and this one parameter for undistortion. So we need 4-point correspondences to solve this problem. This problem was first solved in 2009 using this Grabner basis method. Unfortunately, the final solver was really huge. It was performing Gaussian elimination of a matrix with more than 1,000 rows, so it was really slow. And since then, the problem was revisited several times. And in 2017, we proposed a solution based on some algebraic elimination ideal technique, which performs Gaussian elimination of relatively slow small metrics of size 40 times 50. Still, this solution may not be the best for real-time applications. In 2013, we proposed a solution that uses 5 instead of 4 points. So not the minimal number, but minimal plus 1. And this solution uses two-step approach based on 1D radial cameras. And in this approach, we first estimate the pose up to unknown translation along principal axis. And then we jointly solve for the translation degree of freedom, focal length, and up to 3 distortion parameters by solving very simple linear system. So the final solver is very efficient and runs less than 2 microseconds. And therefore, inside Ransack, it is more efficient than the minimal 4-point solver for large range of outlier ratios, as you can see in this table. So in this case, this is an example of such problem where minimal plus 1 solver is maybe more practical than minimal solver. Recently, we extended this two-step approach to rational radial distortion models of arbitrary degree for both distortion and undistortion. So these distortion models allow for easier computation of reprojection errors in image space than the undistortion models that are used in previous solvers, and are therefore useful, for example, for structure promotion or augmented reality applications. And in 2017, we used the same two-step approach to solve the absolute pose problem for a camera with unknown focal and unknown radial distortion and unknown principal point. So in this case, we need 7-point correspondences to solve this problem. And using this solver, we can register even cropped images downloaded from internet, like images that you can see here. My favorite one is the image of this back with this Notre Dame Cathedral printed on it, where we were able to really localize precisely, even if it's like some cropped image or image on the back. Okay, so now let's move to more complex models. So nowadays, almost all cameras are equipped with some rolling shutter sensors, since they are cheaper and easier to manufacture. Rolling shutter sensors actually capture images line by line. And this leads to distortions when a camera or scene are moving during the image capture, like you can see these distortions there. You know these distortions when you are taking images or videos with your mobile phone from some moving train or plane. So in this case, each line is potentially captured from a different pose. Therefore, the final projection is not a perspective one, and it has to be modeled using a more complex geometry. So since rolling shutter cameras actually capture each row at a different time and potentially from a different pose, camera rotation and translation are therefore functions of the image row or image column. So in this case, image row. And this camera rotation and translation can be decomposed into some initial camera pose at the time of capturing some row R0, for example, the first row or the middle row, and then a motion during this image capture. And in real applications, the translation can be usually approximated by a constant velocity model. And moreover, for realistic motions, it is usually sufficient to linearize the camera rotation around this initial rotation R0. using this first order Taylor expansion. And with these approximations, the rolling shutter projection equation looks like this. So you have this R0 and C0, which is this initial camera pose, and then some motion damping image capture model using this constant velocity model and this first order Taylor expansion for rotation. Still, we have 12 degrees of freedom, and this problem actually leads to very complex system of nonlinear polynomial equations because we are multiplying rotation with rotation, and it's really highly nonlinear equations with a lot of unknowns. So it's not easy to solve it. The first real minimal solution was proposed by us in 2020, and it uses 6-point correspondences because we have 12 degrees of freedom, and several different tricks how to simplify these equations, like hidden variable trick and other tricks. But still, the final solver is quite slow. It runs 1.4 milliseconds. So it's not really useful in real applications inside runtime. So therefore, we also proposed additional approximation for this problem. This is called like double linearized model. So in this model, we use a linear approximation to the initial camera orientation. While camera motion during this image capture is usually small and can be linearized because we have usually quite small rotation during this image capture, this initial camera orientation can be of arbitrary magnitude. So therefore, it can be really far from the linear approximation. But there is one solution, practical solution for this, and this is to compute a rough approximate pose with some global shutter P3P solver, which is usually fast. And if the motion is not too high, it usually gives a reasonable solution for this rotation. And then we can, using this rotation, align the object coordinate system so that the remaining rotation is already close to the identity. And for such, we can use this linear approximation. This solution is, of course, simpler than the single linearized model, but still, it's not really useful for real-time application because it runs something like 0.3 milliseconds. We have something like 5 times speed up, but still not what we want. Therefore, in actually 2018, we proposed a solution where we combine an iterative scheme with fast solver to a system of linear equations. And in this solver, to simplify our equations, we do the following. So in each iteration, so these are our equations, these are quite complex equations. And to simplify these equations, we, in each iteration, fix the camera orientation unknowns in some nonlinear monomials that we have there in this W times V to the estimate from the previous iteration. So after fixing this, we have actually linear equations. So in each iteration, we solve this very simple linear system. And if we repeat this several times using these estimates from the previous iteration, we usually converge to the solution of the original system in a few iterations. And since we are solving just linear equations, the total running time of this solver is something like 10 microseconds compared to 0.3 milliseconds that we had when we were solving the original system. So this is a really solver that can be used in real-time applications, and it really solves this very complex problem for rolling shutter cameras. So let's look at one more problem, actually the most complex problem that you can have, because this is the problem of estimating absolute pose of an uncalibrated rolling shutter camera with unknown focal length and unknown radial distortion. So really completely uncalibrated camera that can be radial, that can have radial distortion, and can be rolling shutter camera, really the most complex model. So in this case, we have 7 degrees of, we have 14 degrees of freedom, so we need 7-point correspondences to solve this problem. And in this problem, even after using this double linearized model, the equations that we have are extremely complex, and they are not really solvable using algebraic methods. The final solver is extremely huge and unstable, and it's not even returning you reasonable solutions. So what we did, in 2020, we actually proposed a solution to this problem. And this solution was based on a similar idea than this iterative linear solver for a calibrated rolling shutter camera. So here, again, in each iteration, we fix some unknowns in these nonlinear monomials that we have in our equations. We fix them to the estimates from the previous iteration. And in each iteration, we again estimate this unknown, so we can iterate this. And in this way, we actually combine this iterative scheme with fast algebraic solvers for simple and tractable systems of polynomial equations. Now we don't have linear equations, we still have nonlinear equations, but they are solvable, such equations. The final solver is relatively simple and fast, and it usually converges again in less than 10 iterations. And in each iteration, it computes or it solves this system of nonlinear polynomial equations using the Grosvenor basis method. And the final, like the solver that solves these equations runs something like 40 microseconds. So the final solver is reasonably fast for real-time applications. And actually it solves something that algebraic methods are not able to solve. So this solver actually outperforms the best competitive solution to this problem, which is actually first calibrate the camera using a global shutter solver, some solver for estimating focal and radial distortion using 4-point correspondences, and then using this calibrated rolling shutter solver together with some local optimization of these rolling shutter parameters and internal calibration parameters and post parameters. And as you can see, maybe it's not so visible, but in this table, the table is showing that this new solver actually returns more inliers and small focal length errors than this type of baseline. And maybe more visibly here on these images. So on the left, you can see an input image with some significant rolling shutter distortion, and then results of these two methods. On the right, you can see the result of our method, and in the middle is the result of this method with this local optimization, where we first calibrate the camera and then use some calibrated rolling shutter solver. Okay, so I think I have 2-3 minutes to talk briefly present semi-generalized post solvers. So semi-generalized post solvers are actually interesting alternative to absolute post solvers in visual localization pipelines. The semi-generalized relative pose problem is actually the problem of estimating the pose of a pinhole camera with respect to a generalized camera consisting of multiple pinhole cameras with known relative poses. So the situation that you can see here on the right. And this is actually a situation that you have in your localization pipeline. So you have one query camera that you want to localize, and then you have several database images with known poses. In contrast to relative pose problems, the semi-generalized relative pose problem has several advantages, and it is that the scale of the translation in this case can be recovered. Moreover, like compared to absolute pose solvers, the semi-generalized pose solvers are using just 2D to 2D correspondences. They don't need 3D correspondences, so we don't need to store a 3D model of our scene, which may be really useful in some applications because you don't need to really maintain this huge 3D model. Of course, there is some trade-off, disadvantage, and the disadvantage is that these problems result in significantly more complex equations than relative pose problems and absolute pose problems. Not so easy even for calibrated cameras to solve this problem. In this case, we need 6-point correspondences for calibrated camera and 7 for camera with unknown focal length. And this problem was solved in 2015, or partially solved in 2015 by Zheng and Wu. However, due to this complex system of polynomial equations, they only proposed solutions to several special configurations of points in a generalized camera. They actually proposed just 2 solvers for calibrated camera and 2 for uncalibrated camera. These solvers, for example, these calibrated solvers, for example, require 4 or more points coming from the same camera of a generalized camera. And actually, 2 out of these 4 solvers are not really practical for real-world applications because their running times are few milliseconds. And these are actually these solvers that can work with more than 2, or can work with three cameras, which is actually this is the advantage of this semi-generalized approach. and it can use 4 points. So the only practical, practical solvers are solvers for calibrated camera that are actually running this standard 5-point relative pose problem solver, and then estimating scale using one more, which is actually not really adding much more information compared to the relative pose solver, and not really using the fact that you have a lot of database images that you can use. In our ICCV 2021 paper, we propose solutions to this problem for planar scenes. So in this case, we need 5 to the 2D-point correspondences to solve this problem for calibrated as well as a camera with unknown focal length. Also, for the semi-generalized homography, we call it semi-generalized homography, the basic, like standard equation, like starting equations are quite complex. So here you can see these equations. So we have the unknown focal length, unknown translation, unknown rotation, and also unknown normal of the plane. However, in our paper, we showed that using the elimination ideal technique and set of variable transformation and clever reparameterizations, we can significantly simplify these equations. If you solve this equation using standard methods, the solver is extremely huge and slow. But after these simplifications, we were able to transform this quite complex system of polynomial equations to really a univariate polynomial in degrees 3 or 5, or for some special case, into polynomials into variables. And in our paper, actually, we propose several efficient solvers that cover all possible configurations of cameras and points. So we can handle configurations where at most 2 points are coming from the same camera, at most 3 points or 4 points are coming from the same camera. And running times of our solvers are a few tens of microseconds. So they are extremely efficient because we are solving actually just this univariate polynomial using efficient Sturm sequences. We tested these solvers in a localization pipeline, and we showed that the proposed solvers are actually faster while achieving comparable accuracy to that of the general solvers, even in the presence of non-planar scenes. Okay, so I think I'm a bit over time. So to conclude, so in conclusion, so this part of the tutorial covered the camera pose solvers, especially absolute camera pose solvers, absolute pose estimation, which is an essential part of many localization pipelines that we will discuss in this tutorial. So we have covered highly efficient solvers for calibrated cameras. For partially calibrated cameras, the underlying system of polynomial equations are more complex, as you have seen. Still, recent progress in developing minimal solvers led to highly efficient solvers even for rolling shutter cameras. So we have really efficient solvers that are running usually few microseconds that can solve these really complex geometries. What is for me interesting, or like maybe it's not so interesting, but unfortunately, many of these advanced solvers, like solvers that are, for example, solvers for rolling shutter cameras or solvers for cameras with unknown radial distortion, are, to my knowledge, not so widely used in applications. So I was thinking why. So I think one reason is that these solvers or these problems were solved in the first paper where these problems were solved. The solutions were usually rather inefficient, and efficient solvers appeared later. And some of these efficient solvers are unfortunately hidden in some papers that are proposing some general methods for improving the efficiency of minimal solvers. So people don't really know that for example, there is this efficient solver for absolute pose problem with unknown focal length, which is hidden in this paper that is presenting a solution to 3 quadratic equations in 3 unknowns. So maybe this is one reason why people are not really using these solvers, and they are not aware of them. I think another important message from this talk is that, as you have seen, for some problems and settings, non-minimal solvers, usually these minimal +1 solvers, are preferable as they are significantly faster than minimal solvers, and their faster running times compensate this large number of iterations that you need to do inside RunSAC. And I think the final note, I want to point you to POSLEAP library, which is a good starting point for finding efficient implementations of minimal solvers, including such solvers that are sometimes hidden in these papers, and you can find them in this POSLEAP library. So I think that's it. Thank you for your attention. I'm happy to answer some questions. How accurate can be the calibration? I think like it depends what do you mean by calibration. So usually these solvers are using, for example, for calibrating radial distortion, these solvers are using this very simple model with one parameter, this is one parameter division model. That one may not be sufficient enough for some applications to have really great precise calibration of your radial distortion. But since this is usually run inside this runtag, and after this you are running some nonlinear optimization. In this nonlinear optimization, you can, with this initialization, you can optimize any radial distortion model, very complex model, and such nonlinear optimization will converge already starting from this model. So these models are usually sufficient enough based on my experience to cover most of the cameras with even large radial distortions. Of course, for significant large radial distortion, they are not so precise, but there are also solvers that can handle large radial distortions with more parameters, and I will show you these solvers also there. So it depends how precise how you define how precise is the application, like calibration. So I can imagine that in some applications you really need to measure things in millimeters, nanometers, and for such applications, the just simple result of such solver may not be precise enough. But after running some nonlinear optimization, which is usually standard, I think the calibration will be really precise.
Noisy measurements where you assume you have 100 parameters, but that's, for example, an headset where the camera can move or the calibration is unsafe, and you want to work out this with the processor.
Yeah, I think in such situations it can be one way how I can imagine that you can do this is that you can at some point where you are already not sure that you are moving away from your calibration, you can recalibrate your camera with running this solver, and then using that calibration again start running faster solver like P3P solver, and then again when you think that your calibration was maybe slightly moved off, then you can again run that solver for uncalibrated camera. It depends also what speed you require. Like also these solvers for uncalibrated cameras are quite efficient. They are really fast. Like they run 2 microseconds. Sometimes maybe for some applications like this AR application, maybe 2 microseconds is not enough. So you really need to move to this calibrated solver. But based on my experience, actually, there are other parts of the pipeline that are usually taking much longer time than the solver itself. So the difference between like 200 nanoseconds and 2 microseconds is huge, but not so huge compared to other parts of that pipeline that you need to do, like inlier counting number of inliers and so on. So it depends really on the application.
Ago, I tried to
There is yes. So my answer. There is a automatic generator of such efficient minimal solvers that was actually implemented by Victor Larsson and his student. That is actually the most recent one, and that automatic generator contains most of the recent techniques that we developed that can really create efficient, more efficient solvers than the first versions of these automatic generators that we had. Still, for more complex problems, just blindly using such automatic generator will maybe not give you the results that you are expecting. Because if you, for example, even if you put to such automatic generator epipolar constraints for calibrated 5-point problem, then the final solver, if you don't do anything else, just put there these equations and say my unknowns are unknowns from this essential metrics, or my unknowns are even unknowns like rotation and translation. The final solver will be really huge and slow compared to what you can reach if you do some pre-processing of your equations. So still there is this need of some knowledge how to maybe reparameterize your equations bit to simplify the equations, to eliminate some unknowns if you can eliminate some unknowns, and then plug them to this software to generate such solver. Yeah. Like, you mean whether we need to be like have still faster solvers? Yeah. Yeah, like it again depends on your application and how you implement it, and whether you need to deal with lot of matches, and or you can somehow sparsify these matches, and you don't need to evaluate in each iteration of ransack so many inliers or compute these inliers, because usually this computation of these inliers is much like it's maybe 10 times even slower than running the solver itself. So it really depends how you implement this. So yeah, I think all these servers that run something like 2 microseconds are, I think, sufficiently fast, and there will not be so huge difference if you will have 2 microsecond or 1 microsecond solver compared to the whole time of the whole pipeline, whole system. But of course, there are problems where you are still not there, and speeding up that solver can significantly speed up the whole process, because especially if you have higher outlier ratios, it also depends on your outlier ratios, whether you need to run that solver just 100 times or you need to run that solver 100,000 times. So this can make also huge difference, and there is really huge job. I had also one slide when I was showing if you need to run the solver really 100 times or 10,000 times, then you are, especially for applications and like this large-scale 3D reconstruction. You think that, okay, I don't need really fast solver because I don't need to be real time. So it looks like, okay, so there is no difference if I have solver that runs 1 millisecond or 1 microsecond, because I don't care about time. But if you run it on this large scale level, where you need to process 100,000 of cameras, and for each camera you need to run it thousands of times that solver, then you are moving from hours to weeks. So but like this standard structure from motion pipeline that we are registering new and new cameras, and this is why there is some huge difference between these 3D construction softwares. Like you have software that can really create such 3D model as you have seen from 30,000 images in a couple of hours, and then you have software where you where you need to wait really weeks. And I'm not saying that it's only because of the solvers, slower solvers. Of course, there are also some other parts, but also the solvers are, there is a huge difference whether you, if you need to run 1 million times the solver, or you need to run it, and you have 1 microsecond, or you have 1 millisecond solver, and you really need to, in some large scale, or in such large scale localization pipeline, to run it 1 million times for all these 100,000 cameras. So there is, even in such applications where you don't really think that, okay, I'm not real time, so I don't need to care, there is a huge difference. To be honest, I don't fully remember. I know I remember that I put there as an application some absolute post problem for a generalized camera, generalized plus scale. One was with this unknown focal length, but to be honest, I don't remember which problems I put in that paper, inside the paper. But I know that Victor Larson actually here implemented that 3Q3 solver, and in his library there are a lot of problems that are actually based on this 3Q3 solver. So it's really nice that in many problems can be actually transformed to these 3 quadratic equations in 3 unknowns. And in that paper we show that if you are solving this, it is also an answer for that Grubner basis question. So if you are solving the system using standard Grubner basis method, or not even standard, like this tuned Grubner basis method, you are still like 100 times slower if you compared to the method where we really manually process these equations, and we're doing some tricks to really reduce the number of operations that are done inside the solver. Thank you very much. So 10 minutes? Okay, so 10 minutes break, 20, what will be 30 break or 25? So unfortunately we are a bit delayed, so we have 10 minutes for coffee break. Thanks. Yeah, sure.
So my question is very stupid. So is it possible to run this code estimation using Google Street? I have a Google Street image.
Yes, definitely. You can run it. So for Thorsten, you have some experience with Google Street images for localization?
The problem with Google Street View images, at least the ones that they release, that they are quite sparse. So Google releases one every few meters.
Yeah.
So if you want to build a 3 model out of this, I think they're not that accurate. But you could put, so you have a problem of so if you want to do, say, P3P or like one of these structure-based solvers where you get 2D, 3D correspondences, then you might have an issue building 3 model in the first place, because they might be too far away to get enough correspondences to triangulate them.
Okay. No, but if I have my own image and Google Street image.
Yeah, you should be able to at least do something there.
I never tried, I didn't try it, but I'm concerned about distortion in Google Street, because nobody knows how they did it. I like ask if I use API and I ask, okay, I need this kind of description.
Time holds. So I'm expecting that it's recording on my PC. I will pause it now. I think no.
A scene model that allows us to project virtual objects into the view of the user as if they were part of reality. For example, let me try to. Sorry about that. Good. And for this, you essentially, this is what you do localization for. Another application is, for example, performance capture, a bit less obvious than augmented reality or robotics. The idea here is that, in this work, we attached a head-mounted camera to a user and had IMUs mounted over the body, and that the camera allowed us to localize the user in the scene without any additional external cameras. And then we could use the combination of the head-mounted camera and the IMUs to figure out the body pose of the human in the scene, which I think is an important step towards like actually modeling humans and scenes and the interaction between humans and scenes. So these are, I think, two interesting use cases of localization. In general, there are multiple ways to subdivide localization systems into different categories. I'm going to present two. It's going to be based on, or three. It's going to be based on how I represent my scene. One way is to do an image-based representation. For example, in the image retrieval part that Jorgos talked about. We have a set of database images with known poses. You have your query image. You try to find like the most visually similar database image, and that gives you an approximation to the pose of the query. You can do slightly better than just doing a nearest neighbor classifier by essentially retrieving multiple images and then interpolating their poses in the hope that this will be closer to the query pose. You can also do pose regression, which is something that Eric will talk about later, where you essentially train a network to, given an image as input, regress a camera pose as output. I would classify this as an image-based representation because in no way it's actually requires 3D data as input or does actually 3D reasoning. You can also, if you retrieve images, you can also try to get an accurate pose estimate. So you can do pose triangulation, essentially given multiple retrieved images and the relative pose between the query and them, you can try to figure out what is the position of the query with respect to the images and these relative poses. So that's going from getting an absolute pose from the image to a relative pose. Similarly, you can train a relative pose regressor that takes two images as input and outputs a relative pose between those images. And you could use it for something like pose triangulation. Or you can do semi-generalized relative pose or homography estimation by essentially establishing 2D correspondences between a query image and multiple database images with known poses, and then estimating the relative pose between this generalized camera and this pinhole camera or this single camera or the semi-generalized homography, as Susanna just explained before the break. On the other side, you can have structure-based or 3D structure-based representations, where you somewhere explicitly or implicitly represent your scene through 3D geometry. This can be some feature-based localization part, which I'm going to talk about, where you have an explicit like 3D point cloud created from images. Given a query, you do 2D, 3D correspondences, and then do pose estimation based on this, as Susanna just explained. Or, and this is something that Eric's going to talk about, rather than explicitly representing the model, can implicitly represent it through the weights of a machine learning model, and then train a machine learning model to regress those 2D, 3D correspondences, and then do pose estimation. Or there's like you can do pose refinement, assuming that you have a reasonable, good initial guess. You can try to project the 3D geometry into the image, try to guess, try to estimate how well it matches, these projection matches the real image, and then start updating your pose in a way that optimizes alignment between image and 3D model. And of course, you can have hybrid things where your underlying representation is a set of 3 points, but you also store those images that store the database images that you used to build the 3D model, and then you first do image retrieval, but rather than taking the position of the image as the data that you're interested in, you store what this image actually sees in the scene, and then you can simplify your matching problem by only focusing on this part. Or you can do hybrid localization in the sense of that you use both 2D, 3D and 2D, 2D matches for pose estimation. This was the image retrieval part, is what Jorgos talked about. This is what I'm going to talk about a bit. And this is roughly Eric's part. We're going to skip pose refinement and hybrid pose estimation in this work. If you're interested in this, drop me an email and I can give you pointers. Okay, and I'm going to start with like classical feature-based methods, go to hybrid methods, and then do pose triangulation, generalized relative pose estimation in the end rather quickly. Well, let's start with feature-based localization. And by the way, if you have any questions, feel free to interrupt me at any point in time. And I'm going to start with what I would call the old school localization pipeline. So the idea is you have some 3D model of the scene. You have your query image, you do feature detection, you do feature description, and you use these feature descriptors to establish 2D, 3D matches by essentially nearest neighbor search in this descriptor space. And then you do camera pose estimation, applying some endpoint pose solver, calibrated or uncalibrated inside Ransack. And that gives you your pose. And I call this old school localization for the reason that like most of these components are rather old. So classically for feature detection, description, you'd use SIFT. SIFT is first published in 1999. For matching, you can do something like KD tree search to accelerate it. That's from the 70s. Or as Susanna said, like pose estimation, like early solutions are from the 1700s. Ransack is from 81. So none of these techniques is really, really new. And you can see examples for these old school systems starting from the early 2000s. And one obvious question is, isn't this a bit outdated? Why am I talking about this? But it turns out that if you look at like modern benchmarks, then these feature-based methods shown here in green are actually still at least competitive, if not better in some cases, than methods that directly try to predict 2D, 3D matches, scene coordinate regressors. And I guess you're going to talk about this also later on a bit. So yeah, I hope that convinced you that feature-based methods are still relevant. So let's talk about them. In order to do 2D, 3D matching, you need to get correspondences. You need to somehow match features that are extracted from images to 3D points. And that works because typically your underlying scene representation is a point cloud computed from images, meaning each 3D point was triangulated from 2 or more images, and you can associate the corresponding feature descriptors from these images to this 3D point, meaning you end up with 3D points plus image descriptors, and then you can do image descriptor comparison between your query features and the 3D points. And the most simple baseline is this: you start with a query image, you extract features, you exhaustively match all your features from the query against the 3D points. You do some sort of outlier filtering, so classic, typically like Lois or the SIFT ratio test that throws away things that are ambiguous. And then the rest you throw into like a standard, like a Ransack with local optimization. And that works surprisingly well in surprisingly many contexts still, especially for small and medium scale scenes where you don't really have strong condition changes. So if all images were taken during day, this works quite well. It gets you state of the art stuff. It can actually also still be efficient, even if you do exhaustive matching just by parallelizing matching on the GPU or multiple CPU currents. So this is actually still like a very valid baseline. But still, let's look at improving this. And where you would improve it is typically the feature matching pipeline. This is typically the part where you want to make sure that you find the right matches and that you don't miss matches that you could have found. So if you want to make this thing faster and reduce memory at the same time, you could use a subset of 3D points. Typically, you don't need all 3D points that you have in a structural motion model. You can be clever about this. I'm going to talk about this briefly later. Or you can, if you want to make things faster, you can reduce the dimensionality of your features. PCA, some learn productions. You can do product quantization. I'm going to also talk about this later. Or if you want to make it more scalable, or if you want to make it faster and more scalable, you can match against a subset of these things. One way to do only matching against subset rather than all is to do approximate search rather than exhaustive search. The common way to do this is something called an inverted index or inverted file. The idea is that you have your descriptor space, you quantize it into individual cells, and for each cell you keep a list of 3D points that fall into the cell or where the descriptor fall into that cell. If you have a query feature, you would search through the nearest cells, figure out which 3D point descriptors belong to these cells, and then only match against those. That's still linear complexity in terms of the number of 3D points, but you typically reduce your constant by a large enough factor that gets like 1 or 2 orders of magnitude faster. And if you want to try it out, there are very good libraries. I can very much recommend Facebook's approximate nearest neighbor search library phase. What you have to deal with is quantization of artifacts. Even if you search through multiple cells, you are still going to miss matches where the query feature and the corresponding 3D point descriptor fall into different cells you're not looking at. Luckily, you can recover this under the assumption that you find at least some correct matches. And the idea is this. So if you have a query image with these features, and let's assume that you match like the pink feature to the pink 3D point, it's a correct match, then likely some of the 3D points closely around that pink point will also be visible in the image. And you can try to recover matches that you missed due to quantization by taking these points and actively matching them against the image. So you go from matching from 2D to 3D to 3D to 2D, and you can do this at essentially limited or no overhead by you store your quantization in a hierarchical structure. So in order to figure out what's the corresponding cell, you need to traverse this tree. Each level in the tree defines you finer and finer subdivision of the space. And when you're traversing with the query features, you at some level remember that, oh, okay, I went through this cell. And if you'd want to do backmatching, so you say you would like to match the 3 points against the image, you know in which cell it is in the bottom level. You just go up a few levels in the hierarchy, figure out, okay, these are the query features that made it into this cell. I'm just going to compare them against it. And then you can do lowest ratio tests or whatever to filter out wrong matches. So this way you can reduce quantization artifacts by essentially exploiting that you have not just a single match, but multiple matches that you can get, and you can recover matches that you lost by proactively assuming that checking whether some 3D point should be visible or not. And you can do this without having to build like additional data structures. So that's a commonly used trick. Another important trick that helps with making things faster and filtering out outliers is based on the so-called visibility graph. When you build a 3D model via structure for motion, you automatically get this graph where one set of nodes is images, the other set of nodes are the 3 points, and you get a link between a camera node and a point node if that point is visible in the camera. And you can use this visibility graph for many things. So for example, if you do this backmatching step that I just described, and you're just searching for nearest neighbors in 3D that you might be able to backmatch, then some of them might actually not be visible because they are like in close by parts that are not visible with the matching feature. And you can use the visibility graph to figure this out and only ignore them when you do backmatching. The other part is like assuming that you have a set of 2D, 3D correspondences, you can try to figure out which of these 3D points are visible together. That gives you a set of connected components. And then you can essentially ignore all 3D matches, 2D, 3D matches that don't fall to the largest connected component. And that typically helps you to remove a lot of outliers. And if you combine this backmatching with co-visibility filtering, then you get something that's called active search that was first published, I think, ECV 2022, so it's 11 years by now. But it still gives you reasonably good performance on some of the standard benchmarks. So the takeaways from this part here are feature-based methods, including using old school SIF features, are still very much competitive. Simple approaches can work quite surprisingly well, especially if you're in easy scenes where you don't have to deal with, say, day-night changes. And this idea of visibility filtering is something that's very useful in general. If you want to know more about old school localization, there's a set of pointers on the slides. We're going to make the slides available later on, and you can check them out if you're interested. These methods based on direct 2D, 3D matching work quite well in small scenes, but they start to struggle in larger scenes or more complex scenes. And the reason is this: if you have like a relatively small or medium-sized scene, then most likely a feature in the image will have like a single corresponding point in the model. So if you do the ratio test, your nearest neighbor will be close, your second nearest neighbor will be sufficiently far away, and the ratio test will tell you, okay, this is likely a good match. If you start looking at large scale, then it starts to happen that you find many 3D points that are in unrelated parts of the model, but that have reasonably similar descriptors, meaning your descriptor space becomes much more dense and your ratio test starts to throw out incorrect matches. So this central assumption of feature-based methods that you have unique descriptors or unique enough descriptors starts to get violated, the ratio test starts failing, and this active search approach that I presented above, which does backmatching, helps you recover some of these things, as long as you find enough correct correspondence in the first place, which will be a problem. And the same thing actually happens under strong condition changes, because your descriptors become very, very different. There's a couple of ways to handle this. One of them is to start looking into more complex outlier filters. One thing that we proposed with Mark a couple of years ago is based on geometric reasoning. The idea is that if you know the height of the camera in the scene, and you have a 2D, 3D match, then your camera has to lie on a circle, and each point on the circle defines the orientation of the camera. And you can use this to do voting by essentially iterating over potential heights, iterating over potential orientations, and that gives you this type of heat maps, which says like warmer colors mean many more correspondences vote for this location and this orientation. That's something that's linear in the number of matches that you can use to figure out which matches are likely to be correct. Another nice thing about this approach is that it actually gives you, through this voting map, some form of uncertainty by looking at how these votes are spread out in space. And it automatically also gives you multimodal distributions. So if you have multiple sides of an image of a building that looks similar, you will actually get multiple maxima in this voting space. And it turns out that you can actually, we did this back then for known intrinsics, you can also do this for unknown intrinsics efficiently. Another way to handle large scale scenes is a bit simpler by essentially saying, I don't need to, in most applications, I have a rough prior where I'm, for example, GPS signal. So you can subdivide your scene into multiple parts. And then given the prior, you only look at these parts that are relevant. And then you do whatever you want to do inside these parts. Both work well. So the takeaway here is that at scale, things start to become much harder than you anticipate, because you get similar structures or locally similar structures at multiple parts of the model that you have to deal with. And you can do this by essentially doing some sort of geometric outlier filtering, doing either this post-voting that I presented, or in using some priors to filter out wrong, like unrelated parts. There's like quite some literature on this topic that I'm not going to go into. But we'll see an alternative to this, which is essentially based on image retrieval. Another topic that I want to, before I get to image retrieval, want to talk about is mobile localization. That's another way of looking at a scalability problem, only that you're not making the scene larger, but you're restricting the compute and memory that you have at hand. So you want to run things on a mobile device, you have to deal with limited GPU, CPU, GPU that you have, limited storage, you have to reduce energy consumption, and you want to be run it in real time. And one way to do this is to say, I give up on trying to localize every frame independently, but I'm combining some local tracking of the camera, visual inertial odometry, or just visual odometry with localization that happens every now and then. So the idea is this. You have some local model that you build on your device that allows you to do tracking with respect to the model, typically some sort of SLAM visual inertial odometry system. And there you will have like some sort of keyframes. These keyframes you try to localize. So you try to estimate the pose of that keyframe with respect to some global model that you have. And then you feed this information back into your local pose tracking by essentially saying, okay, my pose was localized here. I need to adjust my local coordinate system in a way that this fits, or by saying, okay, this on global localization, I observed these 3D points. I need to adjust my local pose so that these 3D points still project accurately into my image. And that essentially allows you to decouple localization and real-time tracking. That enables real-time localization on mobile devices. But that doesn't fully solve the problem. So you still have to deal with limited power and limited compute. And decoupling itself is like allows you to not have to run localization in each frame, but you still have to fit things on device. And you can either do this by having some sort of client-server architecture where you send images to a client and the server, and that server gives you back a pose or other information, which I think Sudipta will talk a bit about in terms of privacy, privacy risks that this includes. Or you try to compress the 3D model in a way that it becomes small enough to fit into your device. Or you could, of course, do both, where if you have store compressed models on a server, that means you can load them faster from disk. And there are simple ways to do model compression. So you could, for example, use only a subset of these 3D points. I'm not going to go into detail how they are selected. Obviously, using a subset of 3D points means I can't localize every frame anymore. There's my mouse. So that's shown here. This is a percentage of frames that I can localize. That drops if I use less and less points. But because I do post tracking in between, I don't care. I don't only need to localize often enough that my post tracking doesn't drift away. So you can actually get from like 130 megabytes to 20 megabytes with this without any degradation in pose accuracy on the device. Here's an example visualization. On the left, it's 35% of the original data, right 5% of the original data. And you can see that you can still localize very, very accurately. But you barely see the difference. You can further compress the map by start compressing the descriptors associated with these 3D points, because that's the part that's typically expensive. And if you do things like product quantization that I'm not going to explain here, you can go from like the 20 megabytes to something like 4 to 1 megabyte without like really seeing a significant increase in your errors. So there's a lot of things that you can do to make things like fit into mobile devices So the takeaways here is that if you want to do things in real time on something with limited compute, you want to combine some sort of global localization with some form of local odometry, SLAM, visual inertial odometry, where essentially the local localization allows you to limit drift of the local camera tracking. And you will probably want to combine this with some sort of map compression, both in terms of structure using a subset of the 3D points and in terms of appearance compressing the descriptors. And again, there's a huge literature on this. I'm not going to go into details here. I will still quickly talk about hybrid localization, where if you remember the simple baseline, where the idea is another way to limit the number of 3D points that you need to match against is to be selective. So the idea is that we're going to use techniques from the first part of the tutorial. We not only store the 3D point cloud, but we also remember which 3D point was reconstructed from which image. If we have this query image, we first use image retrieval to identify the most similar image. We do 2D feature matching between features in the query and features in the retrieved image. And since I know for which features in the retrieved image were used to build 3D points, I get 2D, 3D matches, and I can use this for pose estimation. And essentially, because I only match against like a small subset of 3D points, I don't have to deal with global ambiguities anymore during the matching stage. So this is something that people have been using for a while. Jan Michael had this paper in 2009 that showed that you can build a retrieval-based pipeline and run this in real time on the hardware that was present back then. So this is something that's like not precisely new, but this is something that currently the community mostly uses. And the current state of the art is essentially using like learned components for most parts. So like learned image descriptors for retrieval, learned feature detectors and descriptors, learned feature matches, or some combination of learned feature detector and matcher. And if you want to play around with things, there are two very good toolboxes: the HLOC box from Mark's lab at ETH and the capture box from Naver Labs. And in terms of being robust to condition changes, such as day-night, seasonal changes, like all of the state-of-the-art methods are based on some hierarchical form that use image retrieval and 2D, 3D matching. Okay, last but not least, I want to quickly talk about, I go from representations that use some form of 3D to purely image-based representations, but that still allow you to give you accurate poses. And the motivation is this: like building a 3D model is hard, especially if you do it at scale. Maintaining it is, I guess, a similarly hard problem, because whenever something changes, you need to remove points, add points, and so on and so on. That involves rematching, retriangulation, especially if you switch to slightly better features. So the question is, do you really need 3D maps for accurate localization? Which leads to structureless visual localization techniques, where you don't store 3D points, but you still need images and their corresponding poses. The advantage is that adding an image is relatively easy. You don't need to keep 3D structure consistent. And then you can easily do feature extraction on the fly, so you can switch to whatever feature, local feature that you like. And all of these techniques that I'm present are essentially based on image retrieval. So given a query image, you try to figure out what are the most similar database images. You compute relative poses to some degree, and based on the relative poses, you try to get the absolute pose of the object in the scene, which you can get because you know the pose of the database images in the scene. And there are two simple, like a simple thing is really compute relative poses between the query and each image, average their rotations to get the orientation of the image, and at the same time you get from each relative pose you get a translation vector. So you don't know. So from this image you know that the query image has to be somewhere in this direction, you don't know how far. And same for the other retrieved images, meaning you end up essentially with a triangulation problem. You get directions for where the image, the query image was taken. And based on these directions, you try to triangulate the position. The alternative, and this is something that I'm starting to use more and more, is to actually represent the database images as some sort of generalized camera, and then compute the relative pose of the query with respect to this generalized camera, which gives you the transition, doesn't give you a scaleless transition, but actually give you scaleless translation, gives you scale of the translation, as Susanna explained before. And in my experience, these structureless methods are actually quite an interesting alternative. I haven't gotten them to get like as good results as the current state of the art, but they get close. And I'm currently trying to figure out, together with Susanna, we're actually trying to figure out why this is the case. And one interesting thing that we observed is that it can be more compact to store images than 3D structure with descriptors. So this is one of the reasons why I'm looking into this. And yeah, that concludes my talk. If there are any questions, feel free to ask them. All clarity is removed. Yep. I think you can ask from there or whatever you prefer.
So if you have this setup where you first do retrieval and then you do that process,
yeah,
don't you suffer that sometimes you have maybe very little overlap because you see something visual content that matches?
Yeah.
Maybe a small part getting very crucial.
Yes.
So if you have a SLAM approach where you build three representation, all information is integrated at once, right?
Yes. And I think this is one of the cases where we observe that if you have 3D structure, get more stable pose estimates. Like these methods based on relative pose seem to be less stable in this type of scenes. Yes. The hope would be that because you retrieve multiple images, you get overlap with multiple, and not only a small region, but other regions. But yeah, you can't always guarantee this. And this is, I think, one of the cases where structure-based methods are more accurate. Any other questions? Not, thank you very much. And we're going to go to the next part, which is privacy preserving visual localization.
Okay, so can everybody hear me and see me?
Wait, Sudipta, give me 1 second.
Okay.
I need to somehow get this here.
I think I can share my screen now.
Try to share your screen.
Yeah.
Can you hear Sudipta?
Yeah.
Probably no. Okay. I need to find a way to get you to on the speaker. Let me try to see.
Okay. Okay. Yeah. Let me know if you want me to speak up.
Something like this.
Yeah, but I can't really.
So, this is okay.
No.
This is okay.
Okay. Can you try to say something?
Yeah. Can you hear me now? Is it working? Hello.
Okay, try.
Is it working now?
Nope. No, this is not working.
Oh, and here, if I press this,
Yes, try to press.
I need to plug it somewhere.
I need to see what I can
To your
Wait a second.
USB. Do you have USB there? Yep.
Yes, try to block this in. But I don't think that.
Um,
Now, can you?
hello, yeah, Susanna, can you hear me now?
No.
On the speaker?
No, the speaker. I don't know.
Wait a second. There was some.
Wait, so
You can try to. Do you have an entry for this?
uh,
Can you? I don't know.
hello,
We're currently trying to come.
okay, yeah, just
connect
speak,
it
just to
to-
see if you can hear anything. Mhm.
Can you try to say something?
Yes,
So it goes from this one?
Okay. So should I increase the volume? No?
hello,
Yeah, this is going from this one now.
Yes.
It goes from this one, yeah.
Again?
hello, yeah, hello, check.
Will it be okay for everybody or?
Again, try to say
Hello,
something.
hello, is it, can you hear me now?
In the hand?
Does it work for the audience? Not yet. No. Can we get it to the loudspeaker somehow? I think
Yes.
that's what.
Somehow we can do it.
Yeah,
Can you say something again?
yeah, can you hear me now? Hello, hello, check. Hello, check.
I'll check another.
Try again.
Audio guide.
Hello. I think others in the Zoom can hear. Somebody in the chat just said that they can hear me, but not in the room. So
That's not loud enough.
not working yet. Should I speak louder?
No, this is good, I think.
It's good. Okay. Okay, I can just speak louder. Is this volume okay for everybody in the room? Hopefully it's okay, and I can just try to speak louder. Is that okay, Torsten?
Yeah, this level of noise is good. Don't get louder, please.
Okay, okay, okay. Then let me start then, right? Shall we go ahead and start?
Yes, please start.
Okay, okay, okay. Welcome everybody to the next part. So I'm going to talk about privacy preserving camera localization. It is highly related to the part that Susanna and Torsten have presented. So, but I will start by motivating why do we suddenly talk about privacy? What is the need for privacy? in this research topic. So what has been happening is that as localization and mapping algorithms have improved, they are increasingly being used in in robotic systems. Lots of applications like augmented reality are basically under the hood using localization and mapping to enable the key features. And as these things get deployed in the world, a number of researchers in the field started looking at privacy concerns, which were essentially not studied earlier because in some sense these technologies were still kind of being developed. But as they go into the real world, a few different privacy concern questions come up. So what's happening is that these, as you heard from Torsten, that lots of the feature-based methods are pretty accurate. They get used a lot, but when you go to large scenes, these methods have very high storage requirements. And so to deal with that, you have to transfer compute and storage to the cloud. And as you start storing all this data in the cloud, that's where some of the privacy concerns come from. So in particular, there is this work by Peter Luga et al. From 2019 that first showed very convincing results that it's possible to invert these 3D points and descriptors, the ones that Torsten was talking about. You can revert them, you can invert them to recover very detailed images of the scene. And when you do that, the implication is that some of these images could reveal sensitive information about the scene or the subjects that are present in the scene. So this is really the key motivation behind this area of work. And so I'm going to talk about essentially this problem in two different settings. There's going to be a client setting and a server setting. So the assumption is that there are some client devices like a mobile device or a wearable AR headset. And there are the implications, the privacy implications are different depending on which point of view you take. So first, focusing on the client setting, the general setup is that some map that is pre-computed in the cloud will be shared amongst multiple client devices, and localization is going to run on the device. So in this setup, the privacy question really is that there is some attacker who wants to extract private information. So this is an adversary. They have some malicious intent, and the assumption is that they have access to all the map data that is obtained from the server. And so the objective in privacy preserving localization is to solve the problem where we want to compute the camera pose as accurately as possible, just like you've heard from the previous speakers. But in addition to calculating the camera pose, we want to prevent this attacker from being able to reconstruct images of the scene by inverting the map features. So in this line of work, to solve this objective, we have now seen there are these 4 papers now that have been published in the literature. The first work, I'm going to briefly describe these papers and kind of share the main take-home message from these papers. And so the first paper to propose a solution for privacy preserving localization was the work of Speciale et al., who proposed a new method called a new representation for the map called 3D line clouds. And then they showed that you can use 3D line clouds to recover the camera pose, but at the same time, prevent these kind of privacy attacks. So what was the main idea? The main idea that Speciale et al. Proposed was to take the 3D point cloud of the scene, and then for each 3D point in the scene, they proposed to randomly pick an oriented 3D line with some random orientation, random direction that passes through the point. And then the idea was to discard those original 3D points and keep only the 3D lines. So effectively, a 3D line cloud is a bunch of 3D lines, and each line has a feature descriptor. So you've thrown away the information of where along that line the point was, but you still keep the feature descriptor. And then what Speciale et al., what the paper basically showed was that now, when you have feature points detected in a query image, you can still solve feature matching just the way Torsten was referring to various papers do. Once you have feature matches, instead of 2D to 3D point matches, what you end up in this framework, what you end up are 2D point to 3D line correspondences. So turns out that each correspondence will give you one constraint. And so in the minimal setting, you need 6 correspondences at least from a single image. And turns out that this pose estimation problem is actually well studied in the literature. It's called the generalized relative pose problem. It was first studied by Stavanius et al. And they proposed minimal solvers. And so what is interesting is that this 3D line cloud paper basically transformed the problem into a setting where existing well-studied solvers could be used. In fact, they showed that there are variants of this problem you could solve where you assume that you know the gravity direction, or you assume you're going to use multiple images for querying for the localization query. And all these solvers, again, have been studied in the literature. And the end message of this paper was that there is some accuracy and privacy trade-off, but the trade-off is pretty good. You don't lose a lot, and you can still calculate a pretty reasonable pose estimation, accurate pose using this new method. But 2 years later, there was a paper at CVPR by Celani et al., who basically analyzed the claims in the original paper, the line cloud paper, and showed that line clouds actually do not obfuscate the scene structure as originally claimed. And they showed that it's possible to recover the original 3D points using an automatic algorithm. Their main insight was that when in the original paper, when the 3D lines were being constructed, their line directions were being chosen from a uniform distribution. And this leads to this. In this way, what happens is that you have enough information stored in the line cloud about point neighborhoods that then allows you to find an approximation for where those original points are. So then when you get these approximate 3D points, you can still apply the same kind of inversion attack and recover images of the scene that can be recognized. Even though they may have some artifacts, a human could still look at them and essentially recover private information. And so Celani et al. Also proposed that a possible mitigation is potentially to explore alternative strategies for finding these line directions. And so at CVPR this year, there's a new paper by Lee et al. Called Paired Point Lifting for Enhanced Privacy Preserving Visual Localization. And in this paper, the authors explore one such new way to construct line clouds. And so the main difference here is they construct the line cloud by choosing 3D point pairs and then joining the 2 points to form the 3D line. So what they claim is that the distribution of line directions is now pretty non-trivial, and using a variety of experiments, they show that it's becomes difficult to recover the underlying 3D points using the method proposed by Celani et al. And the good news from this paper is that the new method also still allows you to calculate camera poses as accurately as the original work. So those are the highlights of the main work that has appeared in the literature that deal with the client setting. So now I'm going to talk about localization in the cloud. So if you look at the little diagram on the right side, what essentially is going to happen now is that the devices are going to upload some information to the cloud. The map is going to remain always on the cloud. It's never going to get shared. But the pose of the device is going to get computed in the cloud and will be sent back to the client device. So in this setting, the objective, the setup is now that the attacker or the entity who's going to basically carry out the privacy attack, it is assumed that they will have access to all the query image features. And the goal of privacy preserving cloud localization is to calculate the camera pose in the cloud, but prevent this attacker from being able to reconstruct the appearance of the query image. So the setup here is basically that one where if you are out in the world taking images with your mobile devices, wearable devices, and you take pictures of other people in the scene, what the desired goal here is that you want the system to be able to localize you within that image, but not be able to, on the server side, should not be any way to recover information about these transient objects, people who accidentally get photographed in the images. So in this line of work, there are four solutions that have been proposed so far in the literature that I'm going to briefly review. They can roughly fall into these two categories. In the first category, you have basically, it's similar to the original work of Speciale et al. Called, they refer to as geometric lifting. So what Speciale et al. Did in a follow-up paper in 2019 ICCB was that they, in this paper, the main idea is to apply the same transformation of points to lines, but we do this in the image plane. So in this image, in the middle, you're shown a bunch of feature points. This could be SIFT or any kind of a local key point extractor that gives you these points. And then for each one of those 2D points, we choose a random 2D feature line and then discard the original point. So the feature representation for the query image now becomes a bunch of 2D lines, each of which is associated with a local feature descriptor. So once again, we have thrown away information. So from that 2D point, you basically have two coordinates, so two constraints. And when you relax that to a line, you have thrown away one constraint, but you keep one. You still have one constraint. And this constraint lets you do pose estimation. So the setup here is where you have lines in the image. When a line is back projected, you get a plane. And what you know is that the 3D point in the map has to lie somewhere on that plane. So once again, each feature match will give you one correspondence. You need 6 correspondences to solve for the 6 unknowns. And turns out that this variant of the problem maps into what was studied in the literature and is called the point-to-plane problem. So Ramalingan et al. Have proposed minimal solvers for this problem and many variants. And once again, the high-level summary of this paper was that there are many practical variants of this problem that you could use, where, let's say, the vertical direction or the gravity direction. Once you use those additional constraints, the solvers become pretty efficient and quite practical. And they can be used within RANSAC. So with very little computational overhead, you can still solve the camera pose very accurately and in a reasonable amount of time. And so here's an example, a visual example of what happens when you use this sort of a method. What's shown on the left is the query image. And there's a person in this image that when I refer to as like a transient object, somebody who's maybe accidentally photographed in this image, and you don't want that person's appearance to be exposed. So what happens is, if you use all the features and upload it to the cloud, the adversary would be able to reconstruct the image in the middle. But using the feature line method, what happens is after feature matching, you end up with points whose positions are revealed in the image. These points are all the inliers from pose estimation. And because the transient objects never produce any inliers, their true position in the image remains concealed. So when you run the inversion attack, you do not reconstruct any of the transient objects. So that's why those regions of the image are completely blurred away. So quickly, I want to let's see how much time. I'll try to wrap up soon. So there was an interesting follow-up work by Geppert et al. In 2002 ECCV, a paper that was titled Privacy Preserving Partial Localization. And what I want you to know about this paper is that this was the first paper which actually considered a secondary goal, which was to say that this paper, sorry, I'm not sure why the slides are changing. Sorry about that. But this is the first paper to consider the problem of location privacy. So they're concerned with keeping the location or the pose of the camera private from the cloud. They want to do computation on the cloud, but they don't want the cloud to actually find out about the position of the image. Sorry, it keeps going back. Let me not sure why that's happening. So the main idea in this paper they pursued was they split the cloud into the map into 3 disjoint maps. And in this paper, they explored a different kind of lifting, which was like lifting a point to a plane. In fact, all the planes in one of the 3 subsets share the same plane normal. So they're basically like a bunch of parallel planes. And the three subsets are basically, they all correspond to three orthogonal directions. And what's interesting is that once you have these three submaps, what they propose is a method to solve a partial localization result. So each server would basically allow you to calculate one row of the pose matrix. So when you have the rotation matrix and the translation vector, it's a 3x4 matrix. And so each server will basically give you one of those rows. So it was an interesting idea as a first step to basically try and calculate poses without revealing the location of the user to the server. And then there have been these two follow-up works, which are not really about the geometry, but about concealing the feature representation. The first paper in 2021, so I'm not sure why the slides keep getting forwarded. I'm really sorry. Okay, so the work by Dusmanu et al. Really, the idea here was, again, it was sort of a lifting operation on the feature descriptor. So now the difference is that you're in high dimensional space. You have a 128 dimensional SIFT feature point, and you want to lift it. So the question is, how do you lift it? You go to affine subspaces. So, and then the high level idea in this paper was that you, not sure why this keeps. So the high level idea here was, sorry, I'm on this slide. So you replace your feature vectors with subspaces, and now to do feature matching, this paper proposed a way to do subspace to subspace matching. And again, there was an accuracy privacy trade-off, but there were some interesting results here which showed that you could solve matching and pose estimation without the sort of the server being able to recover the appearance of the image. So in this case, the person's appearance is not revealed by these sort of inversion attacks, because the descriptors on the patches on the face of the person are not revealed. In a follow-up work in 2002 was another paper which tried to do this in a much more in a learning framework. So they posed an adversarial learning problem where they came up with this neural net called NinjaNet, where the interesting thing is that now the features are trained to be such that they cannot be inverted, but at the same time, you can still use them for feature matching using nearest neighbor approaches. So I'm going, in the interest of time, I'm going to move on and mention one last thing at the end, which is that unlike all the papers that I've talked about, which sort of fall into this feature-based pose estimation methods, you're going to hear a lot from Eric about learning-based localization. So one thing to realize is that by design, these learning-based methods do not actually store maps. They typically train some representation, some neural network that predicts poses or other things. So what's nice about them is that by design, they're designed to avoid the privacy issue because they don't store the maps. But it is important to note that in many cases, these neural nets are trained on specific scenes. So every time you have a new scene which you have mapped, you need to train a scene-specific neural network. So to do that, you do need the map at training time. And this part is not privacy preserving. So in this direction, there's some work that we presented last year at CVPR, where this is a learning-based method that sort of still uses a map, but it's really, really small. So when Torsten was talking about model compression, he talked about these earlier methods that pruned point clouds. In this paper, what we did was we essentially came up with a way to heuristically select a number of points in the environment that are salient. So for a medium-sized apartment with 3 or 4 rooms, we had as few as 300 points. And once we selected those points, we trained a simple neural network architecture to then detect these points. So we basically exploited this whole framework for key point prediction or key point regression architectures. We simply reused those for recognizing these scene landmarks and then using PNP for pose estimation. So what was interesting about this approach is that at the time on some data sets, we were able to obtain much more accurate results than existing learned methods. but the accuracy was still, there was still a gap between like a state-of-the-art method like HLOC, which does. The difference from HLOC is that HLOC in these cases was storing several hundreds of megabytes or even a gigabyte of data for the map and the descriptors, whereas our method was literally using less than 100 megabytes, essentially just the neural network and the list of the 3D point coordinates. So extremely compact, but also like there was a sort of secondary advantage that, it's privacy preserving. So to summarize, I've tried to motivate this sort of new sub area within the field which looks at solving the camera pose, and localizing, users or robots within some pre-mapped space. But in addition, there's this additional goal to prevent the image from being revealed, or as you saw in the paper by Yeppert et al., it would be great to be able to not reveal even the location that you've computed. So this problem is going to become increasingly more relevant as these technologies mature and get deployed in the real world. And so at a high level, I've talked about these three directions that have been explored so far. Number one is geometric techniques, lifting points to lines and planes, etc. Then number two is the direction of trying to learn local features or transform features into representations that cannot be inverted. And the third direction, obviously, is trying to look into learning-based methods. And the real challenge there is there something you could do to even train the model in a privacy-preserving setting? So with that, it's the end of my part. And if we have time, I can answer questions now or at the end of the tutorial. So I think, Torsten, you guys can decide if you do questions now. And these are some of the papers, references that are the papers I talked about in my part. Okay. I don't see any questions on Zoom.
Thank you very much, Sudipta.
Yeah. Should we move on and do questions later?
If there are any questions here, I'll forward them to Sudipta and he can answer them.
That would be great. All right. Thank you very much.
If there are no questions, then let's thank Sudipta again. And we'll switch to Eric.
Hello. Hey, there is no audio in Zoom. A bunch of people are, everybody's saying there's no audio. I also can't hear anything.
So now it should work, right? Yeah.
That's good.
Okay, so we have done this tutorial a few years now, and my part has only always been called learning-based visual relocalization. But what does that mean in an age where everything is learning-based? You learn matches, you learn features, you learn everything. So I think the title has to be updated. Okay. To something like regression-based visual localization, I would call it. And what types of regression will we cover? So you can regress different things. You can regress poses, and there are two flavors of this. There's absolute pose regression and relative pose regression. We will talk about that. And there is correspondence regression, also known as scene coordinate regression, and we will talk about that. But to establish some foundation, let's quickly repeat a feature-based approach to relocalization. How does that look? Here is a standard pipeline. Think HLOC, for example. You start with a query image, you have the map built from your mapping images using SFM, for example, and then you do feature matching. First, you do retrieval, so you find the mapping images that are relevant for your query image. Then you extract feature points and you match them. And because you have reconstructed, triangulated the scene, you can look up the 3D location of these matches. This allows you to solve for the pose. Okay, so how do the learning-based, regression-based approaches compare in this framework? So first, there's absolute pose regression. You throw all the steps out of the window and you just train a network to do everything. That's absolute pose regression. Relative pose regression, very similar, but it keeps the retrieval step. And then we have correspondence regression or scene coordinate regression, which is very similar to the feature matching approach, but it only merges feature extraction and feature matching together. The image retrieval part, I left it in here dashed. You can use that to cut a scene into smaller pieces somehow with correspondence regression. It's possible. Some pipelines use it for larger scenes, but it's not necessary, right? It's optional. Okay, when we talk about learning-based pipelines, question is, where does the learning happen? So in relocalization, I would say we have these steps here. We have a preparation stage, we have a mapping stage, and we have a relocalization stage. Think HLOC again. In the preparation stage, you pre-train anything that you want to use. But this is scene agnostic training, and we don't really care how long this takes because we only do it once. You train superpoint, you train superglue, you train netflat. Then in mapping, you reconstruct the scene using your mapping images. So you obtain poses with visual odometry or with SFM. You build a retrieval index, you triangulate the scene, maybe you bundle adjust everything. And here it matters how long it takes because you have to do it for each scene again. And then comes the relocalization stage. You have all the different queries, you register it to the map, and HLOC would do it by nearest neighbor retrieval and then feature matching and pose optimization. Okay, so let's dive into pose regression. And there's a part which is shared between absolute and relative pose regression, namely the question, if a network predicts a pose, how do you parameterize the pose? Why is this part of the tutorial? Because it matters. Here's a study which shows the quality or the accuracy of a pose regression network on the y-axis, training process on the x-axis, and the different parameterizations that you can choose. And you see there's a big difference. So some parameterizations are more suitable for neural networks than others. What are the options? So a pose, 6 degrees of freedom. It consists of a rotation and a translation. Translation is trivial. It's a 3D vector. The rotation, we can represent it by a 3x3 matrix, but there are some constraints. The transpose of the rotation has to, the rotation multiplied by its transpose has to yield the identity, and the determinant has to be 1. And here are some pointers if you want to learn more about rotations, because it's a complicated topic and no one understands rotations really. If they claim, they are lying. So how do you parameterize the pose and particular rotations for the output of your neural network? Well, you could say you predict 9 numbers, which are the entries of the rotation matrix itself. But then you have to ensure that it's a valid rotation, that these constraints are somehow ensured. There are 2 ways to do that. You can actually predict only 6 numbers, which are 2 vectors, and then you construct an orthonormal basis from these 2 using a Gram-Schmidt process. This is one option. Or you predict indeed 9 numbers, and then you use orthogonal procrusts, so SVD essentially, to orthonormalize these 9 numbers to get a valid rotation. You can do that. Another popular option is quaternions. You predict 4 numbers and you just normalize them to make it a valid rotation. That's possible. And there are minimal representations. Rotations have 3 degrees of freedom. Minimal representation is the axis angle representation. So all 3 numbers in axis angle representation will always be a valid rotation. You can also call axis angle representation the algebra of the Lie group SO3 if you want, but it's the same thing. So which one to choose? What's the best one? Turns out that neural networks do not like minimal representations. They like smooth over-parameterizations. So it seems that it's best thing you can do is to actually predict the full matrix and then map it to a rotation. There are many other representations. People get really creative, but in a paper that we did where we tried very different parameterizations, we could only confirm the previous slide. Best thing seems to be to just predict the matrix. Right, another design choice. How do you define your pose loss? For the translation part, it's trivial. It's like a distance between 2 vectors. That's clear. But for rotations, what do? You can actually calculate the angular distance between 2 rotations. For example, the difference rotation, map it to axis angle, then the length of the vector is the angle between the rotations. This is one possible loss. You can also use the Euclidean distance between 2 quaternions, if that's your parameterization. That doesn't correspond exactly to the angle between the rotations, because the angle would be the geodesic distance in quaternion space, whereas the Euclidean distance is somewhat of a shortcut. So you slightly underestimate the errors if the distance between rotations is large. But in practice, it doesn't really matter. You can use that. It's no problem. Same, the chordal distance in rotation space, you can actually just use the Frobenius norm between 2 rotation matrices. It's similar to the quaternion distance. It's a slight underestimate, but it works. And you can also use the Euclidean distance if your Euclidean distance in axis angle space, as this is your representations. All of these are fine, except the last one. That's not great, because it depends on your global orientation of these rotations. So the loss in the distance in axis angle space would depend on not only the difference in rotations, but where that actually is oriented in the absolute space of your scene. And that doesn't make a lot of sense, even though people have used it successfully. But you know, intellectually, it's somehow weird to do that. Last thing, how do you combine translation and rotation errors? You can just add them together and have a hand-weighted weight that you have to tune, but that can depend on the scene. So that's a bit, but there are also adaptive versions of this where a network predicts the weight. And this is formulated in a way where the network would try to decrease the loss, but the weight that it predicts is also added to the loss to somehow calibrate it. And people can show that this somehow adaptively weights the 2 loss terms to minimize the uncertainty of the different components. Read the paper if you want to understand it. I didn't fully get it, but it seems to work. And people use this. So this is a popular choice. There's a different choice, which is attractive, I would say, especially for AR applications. And this is using the reprojection error as a loss and as an error, because it's a natural combination of rotation and translation. So you have a sum over model vertices, and then you project these model vertices into your image using the ground truth pose and using the estimated pose, and you measure the pixel error. There are 2 versions of this. There's a dense correspondence reprojection error, where you project model of the scene itself into the image, and you try to minimize the reprojection error between the scene and the underlying image. You need a depth map for that, or a 3D model of the scene to calculate that. And it somehow mimics an augmented reality application where you would change the scene itself. So imagine I would add a billboard to this shop, for example. If the shop is far away and I add a billboard to that, it doesn't really matter how accurate my position is precisely because it's far away. The reprojection cancels out. And this would be represented well by this reprojection error loss. There's another version, virtual correspondence reprojection error. This mimics placing virtual content into the scene. Imagine the same scenario. The shop I localize against is far away, but I actually place a virtual object close to me. Now my position uncertainty matters again, right? Because virtual object would not be in the correct place. Virtual correspondence reprojection error just defines a grid over possible virtual object locations and then measures the reprojection errors of those. You don't need depth and a 3D model. So that can, depending on the data set, it might be easier to compute. Right, so this was the foundation of pose regression. We know how to parameterize the pose and how to define the loss. So let's see how good these methods are. We start with absolute pose regression. So in our overview here, what you would do in the preparation stage, for example, like PoseNet, you would pre-train a backbone. PoseNet use GoogleNet, pre-trained an ImageNet. And then during mapping, you fine-tune your network with your mapping data. You have mapping images, you have ground truth poses with them. The network is supposed to learn this relationship and forms an implicit representation of the map of the scene. It's encoded into the network. And then at relocalization time, you just give it an image and get a pose out. So how well are these methods doing? Here's a diagram. On the y-axis, you have the precision of these methods, median precision error. On the x-axis, you have time when these methods were published. These numbers are generated on a 17 data set, so something like the MNIST of relocalization, small-scale data set of a few indoor scenes. And we established some reference numbers, right? Active search, so SIFT-based relocalization would achieve 4 centimeters on this data set, median error. And image retrieval, just using the nearest neighbor mapping pose as your estimate, that would achieve 26 centimeters on this data set. So how are absolute pose regression methods doing? We start with PoseNet. It was the first one. It was not too accurate. It used the GoogleNet backbone, quaternion parameterization, weighted pose loss. Then 2 years later, we had an update, which introduced the adaptive weighting in the pose loss, and this yielded quite some accuracy improvement. Concurrent work tried to improve the architecture by using LSTM module. Then we have MapNet, which changed the backbone to ResNet, axis angle representation, more supervision by using relative pose supervision. Then we had, we coming to the age of transformers, so we had works which use attention to squeeze out a little bit more of accuracy. Then we had full transformers applied to absolute pose regression, even a little bit more of accuracy. But this is where we were 1 or 2 years ago. It looked like this. And if you like try to extrapolate, it doesn't look too good, right? We're not really making progress. But then something happened. And we have methods now like Lens, 8 centimeter median error. And we have the FNet, also 8 centimeter median error. So something happened to make progress. What happened? Nerve happened. So view synthesis. You actually train a nerve on your scene, you generate a lot more mapping data and then train absolute pose regression on top. And this makes these methods a tiny bit better. So optimistic view of this chart is we make progress. At some point, we will be at the level of feature matching or maybe even overtake it. Pessimistic view is, well, you know, we have tried for 10 years now, and we haven't even beaten on this simplistic data set. We haven't even beaten feature matching yet. So fast forward, there are learning-based methods which can beat feature matching on this data set. So there is hope, but it's not absolute pose regression. What's the problem with these? So why are they not working so well? This is my take. There's also a paper of Thorsten, which is does a very nice analysis. I would say it's an extrapolation problem. Assume you have just a single mapping image. Your pose regression network can learn the the relationship to the one single mapping post that you have very well. But then if you have query images, you just do a step to the side or you just slightly rotate the image. It looks completely different. All pixels have changed. The global representation is completely different. And the absolute pose regression method it's very difficult for it to understand how the pose changed with respect to the image changes. Local methods like feature matching, active search, agelog, also DSEG, which we will see later, and I would say also NERV, they are local based. They look at patches. And the patches don't change so much. For translation, they don't change at all, or slightly. There are some perspective effects, but slightly only. And for translation locally, these patches also do not change. And these methods only learn to be invariant to these changes, which is much easier to do. That's why APR, I think, are struggling on these data sets. So conclusion, APR, they can be fast at query time if it's just a forward pass to get you to the pose estimate. They are slow at mapping time because you have to train a network. And the accuracy is moderate. We make some progress here. Relative pose regression. They come in two flavors. There is scene-specific relative pose regression and scene-agnostic relative pose regression. Scene-specific, I will not really talk about that because it's basically the same as absolute pose regression. It has the same disadvantages and it's isn't really more accurate. So we see some scene-specific relative pose regression methods here. It's the same bag of methods, I would say. Scene agnostic relative pose regression is interesting though. So what you do is, like RelocNet is one example. What you do is you pre-train an image retrieval method that from a large image collection of mapping images for your query image gets you relevant mapping images. You also pre-train a scene agnostic generic relative pose regression network. It takes two images of the same scene and tells you the relative pose between them. During mapping, you don't have to do much. You don't have to build a representation. You don't have to train anything. You just obtain poses for your mapping images using visual odometry, for example, and you build a retrieval index. Then during relook mapping time, very small, because you don't have to do much. At evaluation time, relocalization time, you get your query image, you look up the closest mapping image, and the relative pose regressor tells you the relative pose of that frame. Combined with the absolute pose of the mapping frame, you get the absolute pose of the query frame. There is one problem with this. Geometrically, we cannot tell the absolute distance based on two views only, as Thorsten has also explained. Not by geometric reasoning, but we could apply heuristics, right? If we assume that the bear is life-sized, maybe, then you could guess that the two views are maybe 1 or 2 meters apart, something like this. It's not completely impossible, but it relies on heuristics. And we see this in experiments. If you train a relative pose regressor scene specifically on this particular data where you want to relocalize, you get a specific accuracy. If you have a scene agnostic one, even if it's trained on very similar data, but not the exact same data, the accuracy deteriorates. But it's also not random, right? Here on this scene, it's 29 centimeters. It works somewhat, but not very precisely. There's a geometric solution, as we have heard from Thorsten. This is triangulation. So you do this relative pose estimation multiple times, which gives you multiple estimates of the translation direction, which allows you to triangulate the pose. This is a geometric solution, which doesn't depend on heuristics. And here we did an experiment on 7 scenes to compare these methods. In circles are single-shot relative pose regression networks, which rely on heuristics. And in triangles are triangulation-based approaches, and the best of these are matching-based. So essential metrics from superglue and then triangulate the poses. This is the best relative pose approach that you can use. But there is something here which I would say is worth investigating. So the 7 scenes data set is oversampled with mapping images. Someone went there multiple times to scan the rooms. You have multiple thousand mapping images for each single small scale room. That's a lot. And maybe that's the reason why triangulation works so well, because you can always, for the query image, retrieve multiple relevant mapping images. That's always possible. So we thought, what if we have fewer than thousands of frames? Let's take 10. 10 random frames to represent each room. The picture changes slightly. We are able with post-regression to beat SIFT, yay, some success, but we still lose hard to Lofter and Superglue. But we can go on, right? So let's use 5 frames. Okay, didn't really change. We can use 2 frames to represent a single room, and then we are able to beat feature matching approaches, which is awesome. But we're not done yet. We can represent a room by a single image, and then relative post-regression is really the only thing you can do. And we win, almost, because there is something else you can do. You can use feature matching, get the essential metrics, decompose it to get the unscaled translation, and then hijack the scale estimate of depth estimation network to scale the translation. And this actually works much better than relative post-regression. But there is something about this plot which is not so obvious. When you go from 1,000 frames to 10 frames to 5 frames to 2 frames, you always need post images. You need the poses of these reference images. And for 5 frames and 2 frames, that actually becomes hard because the 2 reference frames in your room might not have visual overlap. How do you get the poses of these? You might use post tracking, but then you have to ensure continuous tracking while recording these 2 reference images can be cumbersome. But when you use just 1 frame, that actually goes away because the 1 frame gets the identity pose. You don't need poses anymore. So if we go back to our diagram, the mapping stage degenerates to you just take a photo and that's it. You don't need poses anymore. No visual odometry, no SFM. The mapping time is 0. And then the relocalization is just applying your relative post-regression approach, whether it's feature-based or network-based, and you get the pose of that image. You might ask, well, okay, but you can do that in theory, but is it useful? Does that work? Here's an example from the 17th data set. We have a reference image, we have a few query images, and we apply these methods. And these are some qualitative results of a relative post-regression network on the left and superglue with depth estimates on the right. We apply a very coarse reprojection error threshold here, where we say green dots, green estimates, that would still be an okay reprojection error. It's not super accurate, but it could still be useful for some AR applications. And we see there are some green dots, so maybe this can be useful. But arguably, a single room is very hard to represent with a single frame. But there are places like this one, I would say. You can represent it well with a single frame. Or these ones here. And actually, Niantic games are built around places like this. So this allowed us to create a nice data set of such scenes, which are represented well by a single image. We have a data set with 65 scenes for validation, 130 scenes for testing, and 460 scenes for training, relative post-regression. And we hope this is useful, and the community uses this to push relative post-regression forward. We have baselines, evaluation code, leaderboard, everything is online. You can use that. I want to show you some qualitative results to show that this is possible, right? Relative post-regression with respect to a single frame is possible. So here we see an easy scene and results of feature matching with depth estimates. And you see, yeah, somewhat it manages to estimate the pose relatively correctly. This is one of the easiest scenes in the network. Usually it's very hard and doesn't work so well. There's work to be done, but there's hope. And there's also hope for relative post-regression. Here we see an instance where we move around the well, 360 around it. Feature matching will fail at some point. It cannot find matches if the viewpoint change is too big. But the red frustum, you know, if you're friendly towards these kinds of methods, you see that it's able to actually reason about the shape of the object and that you move around it in a 360 motion. So I'm personally excited that if people start working on this, relative post-regression might actually go somewhere. and this might be useful and interesting. So relative post-regression, to wrap up that part, low or no mapping costs. That's why they are very interesting. Scale ambiguity is the key challenge. You will always have to rely on heuristics. And to push forward some research on this, we created this map-free relocalization benchmark. Okay, last part, correspondence regression. This is also something you can do. How does that work? As I said before, it is an approach very similar to feature matching, but it merges feature extraction and feature matching into one step, correspondence regression. You have your 3D scene. You have the query image that you want to relocalize. You say, okay, each surface point of the scene has a unique 3D coordinate in the scene space, and I train a network to regress these. In particular, the network takes an image patch, and for the center position P of the patch, it predicts the 3D coordinate of in scene space. So the prediction induces a dense 2D 3D correspondence field. You can use RANSAC and PNP to recover the pose, and this solves the relocalization problem. How do we train that network? Well, case one, the easy case. You have RGBD mapping data, or you have a 3D model of the scene, which allows you to render RGBD data. If you have RGBD mapping data, you can generate ground truth scene coordinates, and then the learning becomes trivial because you just define a loss between the predicted scene coordinates. The ground truth scene coordinates can be the Euclidean distance. If your if your query images are RGBD images, then that's actually the best thing you can do. If your query images are RGB images, then it makes more sense to optimize a reprojection error, because this is what PNP will also try to optimize for pose estimation. So you can have a loss like this, where up to a certain threshold, you optimize the Euclidean distance to the ground truth, and then to refine it, you switch to a reprojection error loss to get squeeze out a little bit more accuracy. That's the easy one, where you have ground truth scene coordinates. There's also a more difficult one, where you just have RGB mapping images. What do you do? Well, first you can establish some constraints on the scene coordinates. You can say, well, you know, they should be in front of the camera at least. They should be not too far away. They should be not 1 kilometer away. And the reprojection error should not be horrible. It should somewhere be on the ray, near the ray of the pixel. So if they are valid, if they are within these constraints, you just say you optimize the reprojection error. If they are outside these constraints, you try to get them inside the constraints by using a heuristic. And the heuristic just says, well, I don't know the depth of my mapping image, but I can assume an average depth, like 3 meters, 10 meters, something like this. And only if the scene coordinate prediction is completely wrong, I use this prediction to pull it into a good place in front of the camera. And then as soon as my coarse constraints are satisfied, I switch to the reprojection error. The reprojection error is single view only, but during training, the network sees many different views and it learns multi-view consistent 3D coordinates with the correct depth. That means that the network itself recovers the geometry of the scene during training. So here we see how in the beginning of training is basically just a blob. And then by optimizing these reprojection errors, it learns the geometry of the scene. So this is low-level training using reprojection errors. There's also some higher-level training which you can do by optimizing a pose loss. So you estimate poses during training from your mapping images, compare it to the ground truth mapping pose, and backpropagate the gradients throughout the entire pipeline. For this, the pipeline has to be differentiable. So let's walk through the pipeline and see what we can do. First step is scene coordinate regression. That's differentiable because it's a network, right? We have hypothesis sampling. The sampling itself is just a subsampling of scene coordinates. That's no problem. You can differentiate through that or ignore it. The post generation is PNP. There are multiple differentiable PNPs available today. One of them is explained in the DSEC++ paper. It's an analytical approximation to PNP gradients. Then we move into the inlier counting. The reprojection error calculation is differentiable. Then you apply an inlier threshold. You can use a soft threshold and a soft inlier counting that's differentiable. And then you move into ransack. The ransack hypothesis selection is an argmax selection. You select the hypothesis with the highest inlier score. That's not differentiable, but in the DSAC paper, we propose an alternative where we say, okay, you can turn this into probabilistic action. You select the hypothesis randomly according to probability that is derived from the inlier count. The higher the inlier count, the higher the probability of a hypothesis to be selected. This allows you to define an expectation loss. So if I select my hypothesis randomly, what loss do I get? The expectation is a weighted sum. The summons are the losses of the different hypotheses. The weights are derived from the inlier count. So everything is soft and nice and can be differentiated. The impact of end-to-end training is that it allows the network to focus on certain scene parts which are reliable to relocalize against. For indoor scenes, you get a nice accuracy boost of around 5%. And for outdoor scenes, you can slash your medium precision error quite a bit. Okay, let's talk about accuracy briefly. How accurate are these methods? And this is again on the 17th data set. So we start with active search as a baseline. Then you can do ACE-log, which does a bit better here. You can also use R2D2 and retrieval, and then scene coordinate regression. So in this case, scene coordinate regression seems to have higher accuracy. And scene coordinate regression, DSAC star, is also flexible with respect to using depth, so you can use depth and get even higher accuracy. Great. But somehow, didn't Thorsten show the opposite graph? Wasn't it the other way around? Wasn't feature matching supposed to be much better? And now suddenly scene coordinate regression seems to be better. So what's going on? Well, we have to look at the ground truth. How do you generate ground truth? Our data sets fall in either of two buckets. Indoor data sets usually use DSLAM ground truth, Kinect Fusion, to to record your ground truth poses. Or outdoor data sets usually use SFM to generate ground truth poses. And if I would show you either one of those, you would say, yeah, probably fine, looks good, let's use it. But if you overlap them, you see it's not identical. And the question is, what does this do to your benchmark? So here we see qualitative results of active search on the left using DSLAM ground truth, on the right using SFM ground truth, and you see it matters. So on the left, active search looks not that great. You would think, okay, the method sucks, really not good. But if you use SFM ground truth, active search suddenly becomes very accurate, and it's like a state-of-the-art thing which you can do. For DSAC star, scene coordinate regression, it's similar. It's not so pronounced, the difference, but DSAC star actually works better on the DSLAM ground truth. So what does that do to our ranking? It inverted almost completely. The ranking almost flipped. And the worst method is now the best method. And the best method is now somewhere in the bottom. The thing is, it's not clear which ground truth is better. The picture is more complex. It's something like this. And now, well, that's where we stand. The relocalizers are so accurate that we have problems with the accuracy of our ground truth. You can say, okay, I look at both ground truths simultaneously, and then the good thing about scene coordinate regression is, I would say, it somehow seems to be able to adapt to the inaccuracies of each ground truth. So DSAC star RGB version is not best on either of the two, but it's second on both. So seems to be able to adjust a little bit at least. So what's the disadvantage of scene coordinate regression? Well, maybe the training time. So DSAC star spends 7 to 8 hours by optimizing to the reprojection error, and then another 7 to 8 hours for end-to-end training. So this takes a long time. There are some strategies to deal with this. So if you have RGBD queries and RGBD mapping, you can use random forests. Random forests, you can train them on CPU in a few minutes, and they still have decent accuracy. You can also do on-the-fly adaptation. That works in real time. So you build a representation on a generic scene, and then you reuse this representation as you go through a new scene and repopulate the representation, and it allows you to relocalize while you go. That's very nice, but it only works in RGBD. If you have RGBD mapping and RGB queries, you can still use random forests. And there is a nice 3DV paper which shows that with few-shot learning and meta-learning, if you have RGBD mapping data, then you can train scene coordinate regression networks in a few minutes. But in the generic case, RGB and RGB queries, RGB mapping and RGB queries, there was no strategy, right? But that changed with CVPR 23. We have a poster tomorrow about accelerated coordinate encoding, how to make this fast. And it revolves around the split of the network. So we say we have a scene agnostic generic CNN feature backbone, and we just have a scene specific MLP regression head. The backbone maps an image patch to a feature. The regression head maps the feature to a scene coordinate. During training, we just use the agnostic backbone to generate a feature buffer of high dimensional mapping features. This takes around 1 minute on a decent GPU. And then when you're done with that, you just shuffle the buffer. And now you start the actual scene specific training. And this is just an MLP, which allowed us to shuffle the buffer. We pass the MLP a batch of random features, which come from random mapping images. And that means you can optimize the reprojection error, not only over one view, as we did before, but over multiple thousand views. So basically you optimize over the entire set of mapping images, which makes the optimization much more stable than it was before. You can use fast, high learning rates to train these methods. Then at relocalization time, we combine the head with the feature backbone to do scene coordinate regression as before. And this is so stable now that we can do trainings in 10 seconds and still get sensible results. So this took hours or days before, now it takes seconds. And you can still, on easy scenes, relocalize with very nice accuracy. To claim state-of-the-art accuracy, we have to spend a little bit more time, 5 minutes. This is a 200 times speed up compared to DSX star, to the 15 hours that you have seen before. On a consumer-grade GPU, the speed up is even larger, it's 300 times. And yeah, nice accuracy for these methods. So I will wrap up the talk now. I will not talk about the results. Accuracy is high. Now the training time is also good. The memory footprint is also good. For larger scenes, you can split it into chunks of smaller scenes and solve it with an ensemble. And that's also possible now and not so costly because each single model is trained quickly. And at relocalization time, you just push it through all the models and take the estimate with the highest inlier count as your final estimate. There are more intelligent ways to make it more scalable. Instead of using all models for your query image, you can have a gating network which decides which part network of the larger scenes you want to evaluate, instead of just using all of them and deciding by the inlier count. So to wrap up the scene coordinate regression part, high accuracy, so much that we have to look at the ground truth actually to decide which method is the most accurate one. So we are at that level of accuracy now. Memory demand is quite low because the scene-specific network is just a small MLP that we train. Mapping is now relatively fast, a few minutes on a GPU, and you can solve larger scenes by chopping it down into multiple smaller scenes. So this is the conclusion slide of my talk. I try to highlight for each method what has changed recently in 1 or 2 last years. So for absolute post-regression, we made progress on accuracy by using view synthesis powered by NERV. For relative post-regression, we recognize it as an interesting alternative with specific advantages, and we want to drive progress there by having this new data set here. And scene coordinate regression is becoming practical now because the long mapping times that you had to pay previously, they are basically gone. This can be trained fastly now. Thank you so much. Well, so I think we are over time already, so I would maybe not take questions, but you can chat with me anytime.
Okay. Sorry for that, everyone. I hope the slides, for those online, I hope the slides were self-explanatory enough. You'll get the rest of the story. So then how do you get ground truth? So one way is manual labeling, automatic SFM or SLAM. We heard some of the issues with that from Eric. And then you can have custom rigs with additional sensors like laser scanners and so on, and also detailed reference 3D models captured with much higher end systems like laser scanners and so on as kind of a more realistic ground truth. To go back here too. Okay. So we just heard about this problem before. I do have to say that I like the ColMap ground truth a lot better from your own comparison of the background. It seemed to be a lot more. Okay, I see. Okay, good. Right, it's all independent poses, right? I think. Yeah. Okay, good. Okay, so I'll go quickly through a few popular data sets. Cambridge, Landmark, 7 scenes. Those are, they were in particular good to get, post-regression methods bootstrapped. They're representative of AR scenarios. They're mostly small scale and single image queries only. Argente Night, Float Tourism, San Francisco. Those are clearly large scale, very large scale, some of them, San Francisco in particular. But no guarantee of ground truth accuracy. And it's also single images. And also for many of them, the viewpoints are a little bit constrained. Other popular data sets, Inlog, Beidou, Navrolabs, and so on, more indoor data sets. They pushed forward indoor localization. They're good for moving beyond point structural changes. There's some structural changes in there, but there are also challenges here. ETH3D, very accurate, but then not much diversity on a few kind of limited viewpoints, etc. So challenge with all of those kind of summarized here. I'll go quickly through this. I'll come back to that slide later. Also, a problem with a lot of the methods is that they're actually often saturated. So if you look here on the third column, it's all 99% or 100%. And many of the methods are very close to each other. And in the end, the difference is in 1 or 2, images that are kind of, somehow you just make something that solves one image and then suddenly you're on top of the benchmark or things like this, which is obviously not what you really want to be doing because it's not representative. Those things are actually not representative of real world improvements. Okay, so overfitting. Okay, so what I'll talk about now is essentially our effort on doing a new data set, the Lamar data set. So localization and mapping for AR is where it comes from. This is the type of scenes that we've been looking at. So large scale, relatively large scale, indoor and outdoor. When I mean large scale, I mostly mean, even for the church that you showed at the end, it's kind of 4 facades and that's it. Okay. When I mean large scale, I mean a large connected space with many different areas, different rooms, different hallways, in and out and around and things like that. So visually very diverse kind of, many places in the sense of, if you do, let's say, single image relative localization, you need many, many images to build up, like to see all the different places, right? So probably tens or hundreds of different locations within one map. That's what we're talking about. So I feel that's much more representative of many of those AR scenarios. Also, in terms of capture, we both have headsets as well as handheld devices. So both, because you move differently with both of those, the viewpoints are different. So we brought both of those in. These are essentially kind of the trajectories that you see. So going through many hallways and rooms and things like this. This is the kind of imagery that we capture. So we have the images used for head tracking. We have also color images and depth, IMU signals, and also radio signals, which we propose, we want the community to also look more at how to leverage these radio signals like Wi-Fi and Bluetooth and so on as an alternative for coarse localization that can really be helpful and is typically available in those devices. And then for ground truth, we propose actually high-end laser scanner based kind of more survey type level equipment. Okay. So we've given AR devices to about 20 non-experts that we've, essentially had capture over duration of more than a year, go through those sites, go back through the same areas and do natural motions without too much instruction so that we get a lot of diversity in how they move around the space. So those were not AR interactions, they were just meant to explore the space. Here's kind of the specs of how we collected, what we all collected in the data. So we use the built-in head tracking of either in HoloLens or the ARKit tracking to connect essentially sequences of images together, which you get on device. And you see the different sensors. The advantage of HoloLens, if you take the full field of view of the 3 cameras or the 4 cameras for head tracking, you actually have a quite nice wide field of view. Yes, and so we also have IMU, gravity, and all of those signals recorded. For example, here on the phone, we build our own recording app, which is open. There's actually many tools that we built for this, and they're free to use for all of you to build upon, to do your own data sets, or to also potentially augment some of our data sets with other locations if you're interested in doing the effort. But so this allows us to capture synchronously all of those different signals on the devices. The LiDAR reference, we actually borrowed from the Microsoft lab, these type of devices, or we work together between both of my labs, both of my teams, with this kind of Navis device, which is a high-end laser scanning kind of SLAM system device. It's not perfect, but it's certainly much more accurate than just walking around with a phone. So we use this as our reference ground truth system. Here's kind of an example of the locations that we capture. So we have about 2 centimeter resolution, 100 meter range. Per scan, no dynamics in the scan. We capture normals, color, and sensor positions. Here's kind of the 3 locations we've captured. So CAB is the computer science building. AGE is essentially the main building at ETH. And then Lynn is Lindenhof is actually a part of the downtown city of Zurich, this kind of old cobblestone area inside Zurich. So pedestrian area where it was safe to walk around with this kind of backpacks and stuff like that with lasers. So that's outdoor only. The other ones are indoor and outdoor mix. And CAB is over many floors, over the different floors. So here, illustration, a little bit of the data capture. So you see all the different colors are different sessions captured by different people, kind of walking around in those spaces, both in kind of the hallways, the stairs. You see actually here the multiple stairs that were captured, multiple floors, smaller rooms, meeting rooms, offices, as well as big rooms. Here's some more visualizations of all those spaces, quite a diversity of spaces. Outdoors also. Then the main building here, main building is actually very confusing, very symmetric. If you've not been there a lot, it's very easy to get confused because you have multiple symmetries. So also quite interesting in terms of visual aliasing and challenges there. Here's some more examples. Here outdoors. And then here in Lindenhof, kind of visualizing a little bit those areas. This is to show you time of day. So we actually had people go there at many times of day. So different lighting, different times, both in the evening times as well as during the day times. This was also over different seasons and so on. Here's some kind of something that shows you that those places actually do change over time. The main building is used for all kinds of events. Here you see just an example when they had posters set up and so on. And you see also the other areas. Actually, the front of the main building completely changed with construction, as you see there, etc. Okay, the device coverage. So we made sure to both have HoloLens and the iPads and iPhones, both kind of have full coverage on those spaces. So here's then kind of how this compares to the other data sets. So we try to be, we both have kind of large 45,000 square meter roughly covered in really kind of this, many different locations, as I mentioned, per these 3 locations, but within a location, many different places essentially. 100 hours of data, 40 kilometers of walking, handheld and head-mounted devices, lots of additional sensor data. and then solid ground truth. And we estimate essentially, what do I have here? Yeah, it's in the centimeter range, essentially not quite as accurate as some of the ETH 3D data set, but amongst the best accuracies for other ones. So we estimate that we're typically in the centimeter range, actually. Let me show that a little bit further. This is roughly our pipeline. I don't have the time to go into too much detail here. Let me skip for this. We estimate the overlap. Once we have ground truth, we can essentially estimate from the model and the different sequences. We can estimate how well a sequence is likely to overlap with another sequence from once everything is aligned. So essentially, this is what we use for ground truth. This is not that this has no drift, but it has little drift, and so over the scale of 100 meters, it might have a little drift. There are actually methods to go beyond that. But at this point, we essentially use this as ground truth because in the end, it is all about, in a sense, relative localization. When I'm in this room, I care about how precise I am aligned to this room. And at that scale, this device is definitely more than good enough, has essentially negligible drift at that scale. If from this side of the building to the other side of the Congress Center, there's like, 10 centimeter drift. Who cares? This is, like the visual thing will not be affected by that because it also cares relatively. Okay. Just kind of quickly going through some of the steps we do here. We align all of those into a single representation, as you see here. So essentially, all these different points in time that we capture this ground truth data are actually all overlapped, and we were able to work with those models as rigid because the drift was small enough over the size to not have to handle that. If this weren't the case, there's actually methods with ground truth reference points that allows that they can build in to correct for this, but we didn't have to do that. Then how we do ground truth? We essentially, when we get a sequence in, we do an initial estimation of from the device odometry. We find initial poses. We do a rigid alignment of the trajectory. Then, given those initial poses, we do PGO to optimize and to bend it to kind of fit better to the poses we found. Then we do guided localization because now we kind of roughly know where each of the frames is, and so now we look explicitly for matches. And essentially then do a kind of global optimization of all of the images we have to essentially to the reference ground truth model captured with LiDAR. It's with LiDAR, but also with high-end imagery. Okay. So we do that for all of those sequences kind of together. So in particular, we don't do single image by itself alignment, but we use the fact that we have the odometry, that we have all these images together, optimize all of that, and then align it to the whole data set. So that, you see here some of the numbers is pretty large scale. Okay, so this is the slide I really want to show you. It kind of shows you the accuracy of our ground truth based on the residuals in the optimization. And so you can kind of see that we have 99% within 3.3 centimeters accuracy that we estimate. And as you can see, the median is below a centimeter in error for ground truth. Right? These are pseudo ground truth, but pseudo ground truth not with respect to Colmap or something else, but pseudo ground truth with respect to a high-end laser scanner. Okay. So we feel quite confident here that we can measure now the improvements actually of the different methods, and we're looking forward to have you test your methods on our method on this data set.
All trajectories are globally registered with centimeter accuracy by fusing the AR sensor streams with the ground truth laser scans. Despite challenging viewing conditions, the process is entirely automated and requires no manual annotation of any sort. We therefore know the pose of each sensor measurement, but also the detailed 3D geometry of each scene.
And you can essentially see that you have a very rich data set on which I don't have the time to talk about this here, but obviously in terms of multi-view reconstructions, in terms of mapping, et cetera, lots of things this can also be used for that. We intend to release all of the
accuracy can be verified by comparing the captured images with the renderings of the 3D models using color or depth.
To have the full data sets anonymized. But you kind of see the accuracy here of the alignment across time between the kind of ground truth models, and then even night images and other things, you kind of see the visualization. It's not perfect, but it's pretty close. It's close enough for most of our purposes. So let's see here. So here's some additional data, challenges with anonymization. So as I just mentioned, let me actually go through some, let me skip a few of those things. There are there's quite some queries in there that are actually quite hard. So this data set is not saturated. We made sure that this data set would not be saturated from the beginning. We build a baseline with the classical methods. We have not yet been able to do it with the learning-based methods because they've not really been demonstrated at this scale, in the sense of splitting it up and handling tens or many tens of areas within a map and stuff like that. But looking forward to it. So we released it at ECCV, the preview data, the basic data to get started. The full data set, as I said, is still waiting for finalizing anonymization, getting all the faces and license plates and so on, blurred out. We have a license that essentially allows this also for commercial use, for testing, for companies. We used actually in this alignment and generating a pseudo ground truth, we use superglue and superpoint, which might have been an issue in terms of license, but we actually got the clear from Magic Leap. They gave us authorization for the purpose of the data set to have that used, and so all is clear there for everyone to essentially build on this data set. So in data sets, there are some challenges with getting access to Bluetooth and so on Wi-Fi and Bluetooth on iOS devices. Ground truthing, there's challenges. Not everything is perfect, but we feel pretty good about it. But there are plans to improve further. We're also looking forward to have the community, to go beyond the 2 devices that we have now, but actually also have other devices contribute. Like, for example, we're talking to both Meta for ARIA as well as Magic Leap to contribute data and to help us in this effort. We're actually also looking at augmenting this data set with also robots moving around in those spaces, which again have different types of motions, different types of scenarios. So let me quickly go through what we provided as kind of basic kind of baselines for this. You see here all the methods. You've heard enough about them before. Kind of the pose estimation, based on single view and multi-view. Also Wi-Fi. Let me skip for this. Here, same kind of the baseline is essentially similar to how we got our ground truth aligned to the high quality LiDAR model. Sequence localization is then with respect to the 3D point clouds, the sparse 3D point clouds, but kind of a similar one with radio filtering and so on, and kind of essentially a similar pipeline. The key is that we, let me actually go quickly for this. First, I'll talk a little bit about single frame metrics. That's still the default. Everybody talks about, for each image, how precisely to determine the pose. Here's some things on coarse localization, NetVLAD versus, different things fused together, including NetVLAD. You see improvements there in our baseline. Radio filtering actually always adds something, in the benchmark. So it's complementary to the visual localization, in particular in visually ambiguous environments or aliased environments. Here's kind of HoloLens versus phone for single frame localization, superpoint, superglue, and SFM, or mesh, or Lofter, etc. The different imaging conditions also, numbers are different in different conditions. One of the key things we really want to drive home, and why we did this data set also, is that, we believe that the community is misguided to be focused on single image, localization retrieval. Because most scenarios that we care about, be it kind of the kidnapped robot problem, right? The robot needs to localize itself, or AR experiences. they're never single image experience. They or very rarely are. You know, same with Google VPS. You know, you lift your phone, you're looking around, like it's actually, yes, you can start from one image and it's great if you immediately localize, but you know, like in the thing, you're actually doing like this until you get localized, right? So essentially, you have sensors that are, you know, video sensors that are in the world. That's the scenario. Okay, so we should leverage that. We should leverage the fact that if I random picture that looks in a corner that's, you know, confusing, that's not really the scenario. It's more like I keep looking and I want to make the best use of that combined data. Okay, so here we show how you can, you know, as we bring sequence localization, the key metric we look at is how long does it take you to get localized? Okay, so if I give you this many seconds, how many times do you know, like how successful are you? How long is not in terms of compute time, though, right? It's how long in terms of sensor data. If I have a video sequence and my sequence is, you know, 1 frame, and then it can be 1 second, 2 seconds, 5 seconds, 10 seconds, that's the numbers you see here. And that's really what we push as a new metric is, you know, like how well do you do at what times as, you know, sensor, how much sensor data do you need to achieve a level of localization? Okay. And notice this is 10 centimeter 1 degree, which we feel is essentially a good number for AR scenarios. You know, it's kind of a number that makes sense. So that's what those numbers are about here. So you also see it's not saturated. We get about 80% after 10 seconds of 10 seconds of video data, of sensor data. We get to about 80% with HoloLens, to about 70% with a phone. This is if we add radio signals, then we can do even a little bit more. It's still not saturated. We had 85% and 70 something on the phone. Okay, so here's actually to show you, you know, what the different steps bring. This is single image. This is if you use a rig. So HoloLens has not a single image, but actually has multi-camera. So it has much wider field of view if you combine all, you know, there's 4 views, but there's really 3 different views. One is a stereo rig in the center. So if you combine all those views, you actually get much better already, right? It's a huge boost, 20%. If you add radio, it helps a bit. If you do longer sequences, so not only one shot, but now you move around and you keep adding data, that's better. Again, with radio, a little bit better. So you see, and it's consistent, right? That all those things help essentially. If we actually look at, you know, we can evaluate the overlap. And so we make sure that we don't ask impossible things, right? We don't ask to localize when, you know, there's part of the environment that was never seen. But you see, essentially, there's still room. So we, you know, better computer vision methods might be able to get all the way to these 99%. At least there's some overlap in the image data between the queries and the map. Okay, so in conclusion, this was quite a large effort, which we're continuing. We hope to expand and we hope to add more data and more variety to it. If people are interested, also please reach out. And so we're essentially really pushing. We really hope the community will kind of engage in this, and you know, we feel this essentially goes in a direction that we should do in terms of the sequence-based localization, in terms of more realistic scenarios for a lot of the experiences or the things that we actually are working on. And there's a last thing that's a bit different, but I wanted to, you know, shamelessly advertise a conference that I think many of you here might be interested in. So this is 3DV 2024. So many of you might wonder, wait, what happened to 3DV 2023? Well, so we decided to shift it from a fall schedule to a spring schedule. We feel that works better in the calendar. Otherwise, you know, Torsten can say, and Suzanne actually can say all about it. It was very compressed the last time around because we tried to be after the deadlines for ECV or ICCV, after the decisions for ECCV or ICCV, but we want to have the conference be before ECCV or ICCV, which, you know, leaves like no time essentially to do a review job. And on top of that, it falls in the middle of the summer break for everyone. Okay, so what we did, we'll have a deadline end of July. And then, you know, we'll have a much more relaxed schedule. And then the conference itself, as you see, is going to be, no, you don't see it here. It's going to be March 18 to 21, 2024. But so it's really like the next edition. So we didn't skip an edition. We just shifted it by 6 months. But that gives us a much better schedule. It also in terms of deadline. So it's not like one day after the ICCV decision. more time for us to do a good job in terms of the program. And so this first edition in the new kind of time frame, so will be after the ECCV deadline. Will be so that's why we chose it in March. March is still, so this is actually Davos. So it's 3 Davos, essentially DV. Davos is, you can still ski in Davos at a time. This is going to be in the same place, the same Congress Center as the World Economic Forum happens. Very nice room. The hotels should not be too expensive because this is not a holiday period. So during the week in Davos should actually be fine. This is before Easter and after all of the winter holidays. So it should be fine. And for students, we have pre-reserved most of the youth hostel, which has 59 francs. So, you know, like 60 something dollars per night per person, of course, in multi-person accommodation, including dinner. So that should be quite nice. So anyways, I invite all of you that are interested to come over to Davos next year. I think it'll be quite interesting. And especially if you love skiing, you should also have that opportunity. Okay, and I'll leave it at that.
Thank you very much.
Back to